So nutrients are basically substances in food. And those are needed for a few things. They're needed for growth, maintenance, and repair. So most of these nutrients are metabolic fuel. Some of them are essentially for cell structure and molecular function. So within nutrients, there's different classes of them. There are these things called macronutrients. And there are three main macronutrients, and these are large, and the word macro should help us determine this, right? So we're looking at things like carbohydrates, proteins, and lipids. Now, micronutrients are small, and they're only in small amounts, and there are two of these. And those essentially are vitamins and minerals. Essential nutrients are nutrients that must be eaten. And these are ones that the body can't make. Or synthesize from other nutrients, right? And so there's somewhere between 45 to 50 nutrients that are considered essential nutrients, right? Non-essential nutrients are essentially also, they are vital to life. But if not enough is available, the liver can usually convert. So if not enough, the liver can make it. Right? And if you think about it, what else is essential for life? Water, right? So technically, by our definition, it would be considered a nutrient as well. And so when we look and we're talking about what we should eat every day, right? Essentially, the USDA has this thing called My Plate, and it's a guideline representation as portions on the dinner plate. So you can see each one of these is referenced. You have fruits, you have vegetables, grains, and proteins and dairies. And they're telling you about approximately the portion size you should have, right? And basic dietary principle says eat only what you need, right? Eat less overall, eat plenty of fruits and vegetables and whole grains, right? And avoid junk food, right? So though we like it, junk food is no. Now, when we're looking at energy value, because all of this has energy value when we're talking about it, it's measured in what's known as kilometers or kcals. And 1 calorie is essentially the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. So basically, when we're talking about, or you see the big word calorie, that stands for 1 kilocalorie, not a single calorie. So it can be a little bit confusing here. And generally, people say that you should have a 2,000 calorie diet. That's an average, though, and that's essentially average considering age and men. And so it's different based on your age and your gender. So the dietary source is primarily from, so now we're going to talk about are macronutrients. And the first one we're going to hit on are carbohydrates. And basically, carbohydrates, the dietary source is primarily from plants, right? So when we're talking about this, you can get examples of this. Starch is one example, and this is a complex carbohydrates. And you can normally find this in things like grain or even veggies. And that's like I said, this is a complex carb. Other thing that you might have, essentially, an example overall, when we're talking about carbohydrates, we're thinking sugars, right? And you have basically monosaccharides, disaccharides, and polysaccharides. And saccharides is coming from the Latin word that means sweet. And so something like a monosaccharide, you could find fructose, that's in fruit. Disaccharide would be something like sucrose, which you get table sugar, and polysaccharide is a perfect example of that starch at the top. A monosaccharide is also essentially glucose. And so you can find all this stuff in fruits or sugar cane or sugar beets, honey, and milk. Now within, they're also known as sugar or saccharides that are insoluble and soluble, and they're called fiber or soluble fiber. So insoluble fiber is basically something you eat that's called cellulose. And if you've taken a biology class, you know cellulose is what provides vegetables their structure. Cellulose is part of what's known as a cell wall in plants, and it makes it really rigid, or that outside being rigid. So your body can't actually break this down. So it's considered an insoluble fiber. Soluble fibers, a perfect example of this is pectin that's in apples or citrus fruit. And this essentially helps to reduce things like blood cholesterol levels. You can find a small amount of this essentially in things like milk or which is lactose. If you think people say that they can't eat lactose, that's actually carbohydrate, or even this thing called glycogen in meat, which is a really large sugar storage molecule that we use as well. That's made up of a lot of small monosaccharides known as glucose. Uses in body is generally for fuel, and most of it's used by cells to make ATP. Now, if we start when we make ATP, and we're going to talk about this using glucose, and it's converted to the storage molecule glycogen or to fat if we have enough stores of immediate sugar. Fructose and galactose are converted to glucose by the liver if we take those in and then into the circulation, right? Some cells do use fat for energy, but if you think about it, a lot of times when you're about to do a lot of physical activity, they tell people if you're about to work out to eat like pasta and things like that because it has simple sugars that are very easy to essentially convert into usable energy. Neurons and red blood cells use just glucose, don't use fat at all. So if you don't have enough sugar in your body to essentially eat, over time you will lose brain cells and they will quickly die without glucose, which should help you understand when you are studying a lot and you are craving things that are high in calorie or high in sugar like candy and pizza and things like that. It's because your body, and especially when it's using those networks in your brain, it's important that those cells get just straight, simple glucose. Now, dietary restrictions, its recommended daily intake is about 45 to 65% of your total calories. Should consist mostly of complex carbs. So in here, we're talking about things that come from whole grain or veggies. You have to be careful because too much sugar can lead to obesity, right? As well as nutritional deficits, because if you're eating stuff that's high in sugar, it may lack substantial nutrients that you need outside of glucose, right? And American diet for glucose is somewhere about 46% are carbs. And the problem, you normally see higher percentages of this in low income families because these by far tend to be the most inexpensive. So that's the role of carbohydrates in our body. The next thing we're going to look at are going to be lipids, but we're going to do a quick review before we go into there. So if you see, you have summary carbohydrates. We should have about 130 grams of these, 45 to 65% of your total calorie intake. Out of that, about 25 to 30 grams of it should be fiber, helps keep you regular. Complex carbs, things that are called like polysaccharides, are essentially the things that you get from starches that you can find from bread, cereal, cracker, or flour, pasta, rice, or potatoes, anything white. Simple carbohydrates, sugars, they can be monosaccharides or disaccharides. You can get them from mostly disaccharides from carbonated drinks and candy, ice cream, pudding. Fruit, you tend to get monosaccharides from. Vegetables, you as well can get some monosaccharides, or you can get fiber essentially from veggies. If you don't have enough, if you have a deficit, you can get tissue wasting, which that's an extreme deprivation. So you essentially are starving to death. Metabolic acidosis can result from accelerated fast use. So you can actually, this is what happens if you don't have enough carbs and your body starts using fats to supply your energy. If you have too much, you can get things like obesity, which is the phenotype that you're overweight, diabetes, type 2 diabetes, nutritional deficits because you're eating too many carbs and not other kind of nutrients, dental issues, gastrointestinal irritation, and too much triglycerides in your plasma. So the next thing we're going to talk about is lipids and how lipids are used. So basically, the primary dietary source of lipids is this thing called a triglyceride. It's also called a neutral fat. It's most abundant. This is its most abundant form here. So basically, the examples that you have for triglycerides, you can essentially find these guys almost in any fat source that you have. So you can find them in meat or dairy or things like seafood, milk, which again is dairy, nuts, anything like that. So you have saturated fats and you have unsaturated fats. And saturated fats you tend to find in animal-based. Fats. And essentially what these are is when you're looking at the difference between saturated fats and unsaturated fats, it means that these have all the hydrogens they can on their fatty acid tails, and these do not, right? They have where you can add more hydrogens on there. So these saturated fats tend to be not very good for you. Unsaturated fats can be really, really healthy. And these are things that are plant-based. And so you see them in like olive oils and nuts or seeds. Most veggie oils have these as well. So they tend to be better for you. And these guys are generally liquid at room temp, and these guys generally are solid at room temp, which means that that's another reason why they tend to be bad for you, because these guys tend to be the ones that can kind of glop together and cause problems in your arteries. When we're talking about this, there are a bunch of different uses that you can have in your body for lipids. Essentially, they make what's known as adipose tissue. And adipose tissue is the fat that you have, and it's important because it helps for protection, insulation, and fuel stores. You also have what are called phospholipids, which is not what you saw before here. Phospholipids are different kinds of fat molecule that's important in the cell membrane. It gives the cell membrane the property that it has. Now, another important guy here is cholesterol. Cholesterol is a type of unsaturated fat. And cholesterol, you can generally find in things like egg yolks and meat, organ meat, shellfish, and milk. In here, the liver makes about 85% of your cholesterol. So you want to make sure that you're eating well-balanced meals that are not high in cholesterol. So cholesterol is important because, and the reason why we need it, it stabilizes cell membranes. So they allow essentially the cell membrane to stay fluid. On top of that, it's also a precursor to bile salt, which we talked about yesterday, and steroid hormones, because it does fit into the group of steroid hormones. So it looks a lot like testosterone or estrogen, believe it or not. Now, number 4 is prostaglandin. This is also a form of a lipid, and it's important because it helps to smooth muscle contraction. It helps with blood pressure control, and it is also important in inflammation. And we've talked about this a little bit before, that there's a COX-2 inhibitor when you take ibuprofen, and that reduces inflammation because it stops the formation of prostaglandin. Lipids are important because it helps you to absorb fat-soluble lipids. And it is also a major fuel for your liver cells, hepatocytes, and your skeletal muscle. So the American Heart Association recommends that you have about 30% of your meal or less of your caloric intake be from fats. Of that, less than 10% be saturated, and that you have no more than 30 milligrams per day of cholesterol. So that's about 1.5 egg yolks of cholesterol. So basically, you want to keep, really, your goal is to be less than 200 milligrams per deciliter. So this is the role of lipids. And so just to kind of go over these and kind of review really quick again, lipids can be both animal sources such as meat and dairy products and plant sources such as oils from nuts and seeds. Overall recommended daily allowance is about 65 grams. Less than 30% of your total caloric intake should come from them. Now, if you notice, you have different types of lipids on here. Linoleic acid is a fatty acid that you can find in nuts, seeds, and veggie oils. And then you also, that's the omega-6 and the omega-3 fatty acids you can find in fish oil and vegetable oils. And both of these are considered unsaturated fats, and they're very good for you. So the recommended daily allowance for the omega-6 is about 11 to 17 grams, and for omega-3 is about 1.5 to 1.6. And so both of those can help if you help overall. Essentially, if you have too much, say for instance, total animal fats, especially saturated fats, you can have obesity and a risk of cardiovascular disease, specifically things like atherosclerosis. You have the hardening of your arteries, particularly with excess of saturated and trans fats. And we didn't talk a lot about trans fats, but both of these are essentially fats. Trans fats are hydrogenated fats that we've made that essentially we've add hydrogens onto unsaturated fats and made them into saturated fats. So they're just not very good for you. If you reduce the amount of fats, you can get weight loss. Fast stores in tissue proteins start to be broken down to provide metabolic energy. The only bad thing is if you get to where you have not enough fat, you can have problems with not being able to control heat, because some of the heat that when you deplete that subcutaneous fat store, that's the fat that's right underneath your skin, it can lead to excessive heat loss because you don't have that insulation anymore. When you're talking about it being in terms of rules of these other lipids, if you have an excess in dietary omega-3 fatty acids, it can actually increase the risk of atherosclerosis. If you don't have enough, though, you can get poor growth, skin lesions, like eczema, and depression. If you don't have enough cholesterol, and cholesterol, you can get things, like I said, egg yolks, or things like organ meat, liver, kidney, brains. If you have excess of this, it can actually increase blood cholesterol levels and increase LDL levels. And this has been correlated with a risk of cardiovascular disease. Whenever you get the possibility of not having enough, you can risk stroke in certain individuals, right? So cholesterol is important, though a lot of times you don't have to worry about taking a lot of it in because of the fact your body makes it. Now for the omega-6, there are no problems currently associated with taking too much omega-6 or not enough, just with the omega-3s. And that can be really, really healthy with things for So the role of protein. Well, protein, the dietary source for protein, is primarily animal products. And things like egg, milk, fish, and most meats. You can also get things like soybeans that are considered as well as the dietary source of proteins. Now, complete proteins are those things that contain all needed essential amino acids. And I'm going to put AA for amino acids. So an example of where you would find these are like eggs or milk, most meat, as well as soybeans. Incomplete is just that. It lacks something. What do you think it lacks? If you said the essential amino acids, you would be right. So legumes is an example, or nuts, or cereal is an example that you would essentially eat these and would not have all the essential amino acids that you would need. Now, how could you get all the amino acids that you would need? If you're eating something that's an incomplete protein or incorporates incomplete proteins, you can combine things. So for instance, if you take legumes and you combine them with cereal, those two things actually contain all the essential amino acids that you need. And so you can use a couple incomplete protein sources to basically produce complete proteins. So what are they used for again? They're structural materials. So something like skin, right? That's the protein keratin that it has. If you're looking at some connective tissue, then when we talked about that, we talked about collagen and elastin being examples of protein fibers found in connective tissue. And basically, if you have muscle itself, it's made up of proteins. They're also functional molecules. And so when you're thinking later, when we're going over digestion and we're talking about all those different things or proteins that break food down, those are basically enzymes. And there are some hormones. Now the dietary requirements here, basically the needs are reflected by age, size, metabolic rate, and nitrogen balance. The rule of thumb, though, is that it takes about 8 grams per kilogram of body weight that you want to ingest. And the American diet provides more than needed. So when we're talking about complete and incomplete proteins, what we're talking about are essential amino acids. And so if you look at the total protein needs, you'll see here, these are the essential amino acids needed to function. So tryptophan, you guys very much have discussed at some time in your life or another because there's a lot in turkey, right? And so methionine, valine, threonine, phenylalanine, leucine, isoleucine, and lysine are all for adults. Histidine and arginine are common for infants. And if you look at here, if you look at corn, it would be an incomplete protein source along with this bean or legumes. So what you can do is you can combine them together to get all the essential amino acids that you need for proper body function. So there are 3 factors that essentially determine whether amino acids are used to synthesize protein or to be burned as fuel. And so the first is the all or none rule. And so, sorry guys. All amino acids needed must be present for protein synthesis to occur. If they're not all present, then the amino acids are used for energy. Now, adequacy of caloric intake, what that means is proteins are used as fuel if there are insufficient carbohydrates or fat available. And hormonal controls. Basically, anabolic hormones, GH growth hormone, or sex hormones actually can accelerate protein synthesis and growth. So that's another factor that helps determine whether amino acids are used to synthesize proteins or to burn them as fuel. And so in the body, there is a homeostatic state that happens where the rate of protein synthesis will equal the rate of breakdown or loss of protein. And so you have what's known as positive nitrogen balance. And positive nitrogen balance is the idea where synthesis actually exceeds breakdown. And so this is where you see this is normal in children. There's a lot of growth happening there, right? Pregnant women. And for tissue repair. Any situation where you're looking at a lot of cells needing to be made. Negative nitrogen balance is a case where the breakdown actually exceeds synthesis. So examples where you might see this is in stress, burns, infection, any kind of injury, poor dietary proteins, and in starvation. And so if you look, this is just a table summarizing the protein or the summary of protein. So you can see that your food sources for protein either come from complete proteins or incomplete proteins. You can see on complete proteins you have egg, milk, milk products, meat. They give you example of the types of meat and soybeans. And in incomplete proteins, you can see the legumes there, lima beans, kidney beans, lentils, nuts and seeds, and grains and cereals and vegetables. And to end up getting complete protein sources, you can combine a couple incomplete sources. Now, the recommended daily allowance, again, for adults is 0.8 grams per kilogram body weight. This is about 12 to 20% of total caloric intake. If you have an excess, so the problems that can arise from that is obesity, you can have enhanced calcium secretion and bone loss, and high cholesterol levels in the blood and kidney stones. Deficit, of course, profound weight loss, and tissue wasting. There is a certain amount of protein that you need to make sure that your muscles stay strong. Retarded growth in children, so if you're not getting enough of these proteins that incorporate essential amino acids, then you're not going to get the proteins needed for structural and functional mechanisms in the body. It can also cause edema due to the deficit of plasma proteins, and during pregnancy it can cause miscarriages and premature birth. So the next thing that we're going to talk about are vitamins. These are organic compounds that are crucial in helping the body use nutrients. Most of the time they work as coenzymes. And a coenzyme is something that helps with the function of an enzyme. Now, most vitamins need to be ingested. Not all of them, though. There are two types of vitamins. There's water-soluble and fat-soluble. And so, let's talk about water-soluble and fat-soluble. So water-soluble basically means that these guys are going to be polar because they can be mixed with water. So the B complexes, vitamin C, are all absorbed with water. B12 as well, but if you remember, B12 needed intrinsic factor in order for it to be absorbed. These guys are not stored in the body. If they're not used within 1 hour, they're removed or excreted. Fat-soluble vitamins are those that actually, these guys, so this is polar, these are non-polar, which means they love lipids. So vitamins A, D, E, and K are all absorbed with lipid digestion products. These are all stored in the body. Vitamin K is not. Now, it's like anything, they can be stored in your body, aka in your fat stores. So if you consume too many, they can cause health problems. Now, as you can see, most must be ingested for vitamins, but not all. For instance, vitamin D can be made in the skin. And this is if you have a newborn and they're having issues with jaundice or they're starting to turn yellow, you can take them outside and get them to absorb some of the sun, and that will help with this. Some vitamin B and K vitamins are made by your flora in your gut, aka bacteria. And things like beta carotene, which you find in carrots, right, can be converted to vitamin A in your body. Just to let you know, there is no one food group that has all the vitamins you need. So, are excess vitamins good for you? So, for the big answer for that is not necessarily. Mega doses of vitamins are useless. And some of them actually cause health problems. It just depends on the vitamin itself. Now, they can be good for you. For instance, dangerous free radicals are generated during normal metabolism. So vitamins like C, E, and A, and mineral selenium, these are all antioxidants that neutralize these free radicals. And so, for instance, broccoli, cauliflower, Brussels sprouts are all good sources of vitamin A and C. And the water-soluble vitamins, if you eat a lot of those, it's not going to be so much of a problem. You're not going to use them all. So you're basically paying money to buy vitamins that you're just urinating out later, right? But some of these that are fat-soluble, you can have serious health complications from them. So it's better just to stay within the recommended daily allowance. And so you can see here on here, vitamin B1, which is known as thiamine. You can normally find that in things like legumes, peanut, whole grains, and pork, right? And here they're a coenzyme, which means they essentially are helping enzymes work. A coenzyme is a non-protein compound. Right? And it's used to remove carbon dioxide from organic compounds. Now, if you have a deficit or extreme excess, so here is a deficit, right? Beriberi. And this is a nerve disorder. It's caused by tingling and poor coordination and reduced heart function. And so you see a lot of this. This is pretty rare in the United States. It remains a constant problem in the sub-Saharan Africa. It tends to break out a lot in the refugees camps. And this is something that's been basically talked about or described for thousands of years in places like Asia. And it became more common with increased basically production of rice. Now, vitamin B2, riboflavin, you can find this in grains, vegetables, and dairy products and meat. It's components of coenzymes like FAD and FMN. And these guys, along with vitamin B3, if you see lysine, that you can find lysine in nuts, meats, and grains, they're components of coenzymes as well, NAD plus and NADP plus. All of these are electron carriers, some for which you will see in the electron transport chain or being produced through cellular respiration. And so riboflavin or a vitamin B12 deficit can cause skin lesions such as cracks at the corner of your mouth, where B3 can cause skin and gastrointestinal lesions and nervous system disorders. An extreme excess of niacin can cause liver damage. So, and this is the first situation that we've looked at where extreme excess can cause issues. Now, B5, again, is a component of a coenzyme A. Coenzyme A is really important in what's called the intermediate step when we talk about going from glycolysis to the Krebs cycle. You can find this in most foods. And a symptom of the deficit of this is fatigue, numbness, tingling of the hands and feet. B6 you can find in meats, vegetables, and whole grains. It's a coenzyme used in amino acid metabolism. So you can get convulsions, muscular twitches, anemia, irritability if you don't have enough, an unstable gait, numb feet, and poor circulation if you have too much. B7 you can find in mostly vegetables, meat, and legumes, beans. It's a coenzyme in the synthesis of fat, glycogen, and amino acids. Here you can get neuromuscular disorders or scaly skin inflammation. B9 you can find in green vegetables, oranges, nuts, legumes, whole grains, and again, coenzyme in nucleic acid and amino acid metabolism. It can cause anemia and birth defects. Having too much may mask deficits of B12. B12 you can find in meats, eggs, dairy products. It's a coenzyme in nucleic acid metabolism and maturation of red blood cells. Again, lack of it can cause anemia, nervous system disorders, numbness, and loss of balance. So you can see with this, if B12 is important with red blood cell maturation, if you remember, you needed intrinsic factor to be able to absorb that having too much B9 can actually mask this. And so you can essentially have problems with making nucleic acids or allowing red blood cells to become functional. Vitamin C, most of us know you can find those in fruits and veggies and other citrus fruits, broccoli and tomatoes. It's used in collagen synthesis, so it's important in making bone and cartilage and generating your gums, and it is an antioxidant. It can cause scurvy, which is a skin degenerative disease, along with teeth and blood vessels. You don't really see scurvy anymore. It used to be very common during the move from the European countries and Africa over here, where they were on ships for a very, very long time, and they did not have adequate supply of citrus. It's not really so much a problem anymore. You can get weakness and delayed wound healing from that. And too much, you can get gastrointestinal upset. Vitamin A, you can get it as a provitamin in beta carotene. And you can get this in orange vegetables and deep green veggies and fruits and retinol and dairy products. And it's basically important to help be a component of visual pigments. It is an antioxidant as well. And so if you don't have enough of this, it can lead to blindness, skin disorders, and impaired immunity. But too much can give you hair loss, blurred vision, liver and bone damage, headaches, irritability, and vomiting. Okay. Vitamin D deficiencies, we know that you can find those things in dairy products, egg yolks, and like I said, it's made in human skin in the presence of sunlight that can help protect against jaundice, especially in children, babies. It aids in the absorption of use in calcium and phosphorus. We talked about this last semester when we were talking about ossification. And so it's common, if you don't have enough, that it can create rickets in children, and these are bone deformities, and it leads to bone softening in adults. Too much of it, though, can cause brain and cardiovascular and kidney damage. And vitamin E and vitamin K, you can find these mostly in veggies. Vitamin K you can also find in teas and colon bacteria. Where vitamin E, it's basically nuts and seeds. Vitamin E is an antioxidant, so it's going to help protect cell membranes, and antioxidants are important, especially when we start talking about mitochondrial function, that over time it starts to wear out and produces more and more free radicals. Vitamin K is important in blood clotting. We talked about that earlier in the semester. And so without enough vitamin K, you can get defective blood clotting. But if you have too much, it can cause liver damage and anemia. And basically vitamin E deficits can cause degeneration of the nervous system. So the biggest thing you can see, vitamins are really, really important. And you can see vitamins are non-protein molecules, right? They are basically necessary to help enzymes function correctly. And you can see in all these cases, or overwhelming majority of these, especially with the B vitamins, that they're important in making the important components of our body, or responsible for helping enzymes work, that important in making energy or important in making certain molecules in our body. And having the right amount is essential. So minerals. There are 7 minerals that are required in moderate amounts. So for instance, calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium are all required. Others work in trace amounts. And basically, they work with nutrients to ensure proper body function. And so basically, their uptake and their excretion are balanced to prevent toxic overload. And so basically, things like calcium and phosphorus and magnesium are all important in hardening bones. And the magnesium is magnesium salt. That's there. right? It goes in a combination. If you remember, iron is important because it's essential for oxygen binding in hemoglobin. Iodine's important for thyroid function. If you remember, sodium and chloride, they're important for, or are the major electrolytes in the blood. They keep the homeostasis of blood in place, and they're also important in neuronal functions. And so some of the foods that are rich in minerals are mostly veggies, beans, milk, and some meat. And this kind of gives you an idea of the deficits, the major function in deficits. Like I said, calcium and phosphorus are important in bone formation, right? And not having enough of these can cause retardation in growth, possible loss of bone mass, or weakness in the bone itself. Sulfur comes from a lot of different protein sources, and basically it's the component of certain amino acids. For instance, cysteine is an important amino acid that contains sulfur. And so if you don't have enough sulfur, you'll get symptoms of protein deficiency over time because you're not going to have the right amino acids to make all the proteins you need. Potassium can be found in meats and dairy products, a lot of fruits and vegetables. They're important in nerve function and acid-base balance. So you can get muscular weakness, paralysis, nausea, and heart failure if you don't have enough of these. And when we talk about electrolyte balance, we're going to talk about all of these again, right? So I'm mentioning them here because they overlap in several sections, some for which we've already covered. Chlorine and sodium, both parts of table salt, you can get that, are important in acid-base balance, water balance, blood pressure, gastric juice formation, nerve function, osmotic balance. You can see all of those are really important in the body. And you can get reduced appetite and muscle cramps if you don't have enough. And then magnesium is a cofactor. And so with this, it's important in ATP bioenergetics, right? And without it, you can get nervous system deficits. So this is just basically a cofactor, is a substance other than the substrate. So something that is not being worked on by an enzyme that is important in the function of that basically enzymatic function. So cofactors are mostly metal ions, and most times they are inorganic or organic chemicals. And so these are going to assist during the actual catalytic process of a reaction. And so these guys are going to bind to proteins or enzymes to help. They can also bind to cofactors. And then, of course, iron is important in the components of hemoglobin and electron carriers in energy metabolism. And they can be energy or enzyme cofactors. And so, of course, you can get anemia and weakness and impaired immunity. Zinc. Well, we already know fluoride is important for maintaining tooth structure. So without it, you can get a higher frequency of tooth decay, right? And you can find this, we fluorinate our water now. You can get it in tea and also seafood. Zinc, you can find in a lot of meats and seafood and grains. It's a component of certain digestive enzymes and other proteins. So if you don't have enough, you can get a failure of growth or skin abnormalities or reproductive issues. Copper is, again, a cofactor in iron metabolism, and it helps to produce melanin. And if you remember, melanin was important in helping to color the skin to protect it from UV rays, right? It's also important in electron transport, and so you can get anemia or cardiovascular abnormalities from these. Magnesium, again, can get abnormal bone and cartilage growth, and it's a cofactor. Iodine, found in salt in seafood. They ionize salt now. That's the reason why we don't really have those problems. And we've already talked about this guy before too. It's a thyroid hormone or a component of it. And basically you can get goiters or enlarged thyroids that can push again the other areas and cause problems, collapse of your trachea if it gets too large. We don't really have this problem over here since we iodize our salt. Selenium is an important cofactor for antioxidant enzymes. Not having enough, you can get possible heart muscle deterioration and pain. Chromium is important. It's involved in glucose and energy metabolism. So your rate of glucose metabolism is impaired if there's not enough. And molybdenum is also a cofactor, and it has disorders in excretion of nitrogen containing. Let's talk about how our body can take those items and make energy from it. So basically, we have enzymes in our body that work to produce the overall effect known as cellular metabolism. So what are enzymes? What do they do? And so an enzyme is basically a protein. There are instances where they can be RNA, but they're very, very rare. They're mostly proteins that help to lower what's known as activation energy. Activation energy is the amount of energy to start a reaction. And what this can do, it can help to speed up chemical reactions. Now, cellular metabolism are all the chemical reactions in the body. And so they can be basically anabolic or catabolic. And we're going to talk about what these are. Now, cellular metabolism, when we go through these, it has two main functions. It can provide energy for our body, and it also helps to make proteins. So anabolism or anabolic processes are when we build larger molecules from something that's small. And so since we're in the body, we're going to focus on building carbohydrates, lipids, and proteins. So when we're talking about carbohydrates, what are they built from? What are the individual types of molecules that carbohydrates are built from? Monosaccharides are simple sugars, right? Lipids, which are fat, these are triglycerides, right? This is fat or a lipid. They're built from glycerol and fatty acids. And proteins, it's monomer. This is basically their monomers, right? Their building units are made from amino acids. If you've taken my class before, this is all review. We've gone over all of this. So what kind of reaction actually takes these small monomers and makes them into polymers, or a larger molecule made up of smaller molecules? It's dehydration. And so this is a synthesis reaction, right? That helps us to make or build macromolecules or polymers. So carbohydrates, lipids, proteins. And what they do is basically we have water leaving to allow two molecules to be together. Now, catabolism has to do with breaking down molecules into smaller. So most of the time when we're like, oh, my metabolism is awful, we're thinking about how fast our body processes food and breaks them down. But technically, metabolism is all the reactions in our body combined. And then catabolism is more specific, that you're thinking about is breaking those molecules down. And so when we're talking about carbohydrates are broken down from, so the largest carbohydrates that you might say are polysaccharides. Those are many, right? Or disaccharides. And so basically they're broke down from these larger entities into monosaccharides, right? And when we're talking about triglycerides are broken down. Basically, these are the energy unit. And so you might have large amounts of fat put together, and that's why bile is important, because it's going to emulsify fat. And then it's going to be able to take things like triglycerides and then break them down even further. And proteins, known as polypeptides, we can basically break large entities right down into amino acids. So carbohydrates, we're getting it, as you remember, from things like sugars, pastas, food. Triglycerides, fats, you might find in burgers or fatty meats. Proteins you'll get from meats and beans and things of that nature. So when you're talking about breaking things down, what reaction do we use to break them down? Maybe you remember hydrolysis, which is a decomposition reaction. The other one was a synthesis reaction. This is a decomposition, right? It takes really large molecules and breaks them down. And we need water to do this. So I think hydro as in water, break it down nice. And so, cellular metabolism includes hundreds and hundreds of different reactions. And they're all controlled by enzymes. So when we're talking about all those things, we mentioned two big words. We mentioned cofactors and coenzymes. And so cofactors are non-protein components. These are going to help the active site obtain appropriate shape. 30. So we've mentioned earlier, you can have ions like copper, iron, or zinc. All of these can be cofactors. No, coenzymes, these are just small molecules. And this as well is going to help with the shape of the active site. And just like before, help the binding enzymes to bind substrate. So basically you have some molecule right here, and then you're going to have an enzyme. And this molecule is going to fit inside here. And become an enzyme substrate complex, basically. And then that enzyme is going to do something to this. Maybe it ends up breaking it in half into two different molecules. And so these cofactors and coenzymes are going to go on here and attach to it. It's all a difference between, are they something like a mineral, or an ion like copper and iron or zinc, or are they a small molecule that helps to do this? Now, again, this all should be review. How does denaturation affect enzymes? And basically, denaturation is a process of breaking them down, right? They lose their shape. And so on here, there's different things that can cause it. A big example that you might see in our body is excess heat. And so 45 degrees Celsius is going to inactivate proteins, and greater than 55 is going to denature them, which means it's going to change their shape. So excess heat can do it. Radiation can do it. Thus radiation sickness, right? Electricity can do it. Certain chemicals can do it. Extreme pHs can do it. And poisons can do it. So if your enzymes aren't working right, you can't make important components in your body, and things such as structural components, but a big part of it, you can't also make energy. And so there's two main ways of making ATP. And it's either through cellular respiration or substrate level phosphorylation. So cellular respiration is a catabolic breakdown. So we're going to break things down, right? Where food that we eat is turned into ATP itself. And it's done that because we start with this molecule called adenosine diphosphate, and we make adenosine triphosphate from this process. And it's a lot of reactions. RxN is a shorthand for reactions. Now you can also make ATP by what's called substrate level phosphorylation, and that's just when you have something like ADP, and this other molecule will have this really high energy phosphate, and it just puts it straight onto it to make ATP. So these are the two main ways that we can make ATP in our body. And so, if you look at it here, cellular metabolism has a few different steps. The first step is glycolysis. The second major step is citric acid or Krebs cycle, and the third is oxidative phosphorylation. There is a step in here that's called the intermediate step that I always talk about as being an individual step, but most of the time they don't talk about it as being a step. So as you can see in here, depending on your food source, whether it's proteins, carbohydrates, or fat, it can provide a starting material in different stages of these particular parts of the cellular metabolism pathway. And so for proteins, basically certain amino acids are broke down. You remove the amine group here, and then they can fit into either glycolysis. They can be that intermediate starting product, or less frequently, they go into the citric acid cycle. If you have carbohydrates, it's going to be broken down into two things, right? Basically, either you're going to go, actually, strike that. Carbohydrates can be used as glucose, and other sugars can be converted into the stored glycogen, but glucose itself can go straight into glycolysis, which is why they tell you to basically carb load, because this is going to get, this whole sequence is going to give you the most maximum amount of energy for the least amount of buck. And then fats can be broken down into two components, glycerol and fatty acids. Together they make triglycerides. Separate, glycerol can fit into glycolysis. Basically, when we talk about it, it's the area where you will see the ugly and hot stepsisters, or it can feed straight into this intermediate, right? And then as you can see, the brunt of ATP gets made down here in oxidative phosphorylation, and this is where we'll make water, metabolic water, and it takes oxygen to do so. And one of the big waste molecules out of here, of course, is carbon dioxide, and we'll talk about that.
Glycolysis can occur without the presence of oxygen and takes place in the cytosol, or the fluid found in the cytoplasm of cells. In we humans, glycolysis often provides the energy for events such as 100-meter dashes and weightlifting that require short bursts of energy. These types of activities depend on glycolysis because they happen so suddenly that the cells of the body cannot be oxygenated rapidly enough by the heart and lungs to support the second means of converting glucose into energy, cellular respiration, which requires oxygen. Glycolysis is not a very efficient process. It only releases approximately 2% of the energy stored in a molecule of glucose, which translates into about 2 ATP molecules produced for every glucose molecule metabolized. Fortunately, cellular respiration provides a much more efficient way of using the energy stored in the glucose. But as a distance runner's gasping for air suggests, the process of cellular respiration is highly dependent on the availability of oxygen. Cellular respiration converts approximately 37% of the energy stored in a glucose molecule into immediately usable energy in the form of between 36 and 38 ATP molecules. While this does not sound like a tremendous figure, it is more efficient than either automobile or jet engines are at converting their respective fuels into usable energy. Most cells can metabolize a variety of organic molecules other than glucose for energy, including more complex carbohydrates, proteins, and fats. But in this program, for a number of reasons, we will focus specifically on how cells convert glucose into energy. First, the cells of most multicellular organisms at some time or another burn or metabolize glucose and convert it into energy. And many types of cells, such as the nerve cells of the human brain, burn glucose nearly exclusively. Secondly, when organic molecules other than glucose are used in cellular respiration, they are usually broken down and converted into glucose or similar molecules before undergoing the process of cellular respiration. Finally, it is useful to visualize cellular respiration as a set of reactions that reverse the reactions involved in photosynthesis. And photosynthesis is usually explained in terms of synthesizing glucose molecules from carbon dioxide and water molecules in a process powered by light energy, even though other carbohydrates can be synthesized via photosynthesis.
So, when we make ATP, the creation of it and the breakdown of ATP is reversible. So for the most part, we start with a molecule called the adenosine diphosphate. And you can see it has a sugar here, it has that adenine, and then of course it has two phosphate molecules. So whether we're doing cellular metabolism or substrate level phosphorylation, what happens is a phosphate comes in here and it gets added. And so this is what we make ATP, and we have this molecule because it's much like if you were going to go out into the world. It's really hard if I'm going to go to McDonald's or basically Chick-fil-A or any of those places or gas station and have a $100 bill or my paycheck. They're going to look at me like I'm crazy. They're not going to want to take it. Or if I go here in my office and at the end of the hall I have a machine that allows me to get treats. If I go and try to put a $50 bill in that snack machine, that Coke machine, it's not going to treat it accordingly. So we need to have a functional bill, a 1 or a 5 or a 10. So the creation of ATP is much like taking glucose or these other big entities that are like your paycheck or like a $100 bill, and then breaking it down into smaller components so that your body can use it and not have to waste a lot of it, right? And so ATP is that component. And basically what happens is that all that energy that we're going to talk about is stored within that bond when we go and kind of break it, and then it releases it when the chemical reactions at the end of the molecule are stabilized. So you go back and forth. So you're not making ATP from scratch. You make your body weight in ATP every day. So it would take way too much material and time and energy to do that. So you basically circle back and forth between these two molecules. Now we do it and make ATP through cellular metabolism through a set of what's called oxidative reduction reactions. And these are important chemical reactions that are part of cellular respiration, and they're needed to release energy from molecules so it can be converted into usable energy. And so basically this whole part of oxidation reduction follows or satisfies the law of conservation of energy. And so the law of conservation of energy is that basically that energy is conserved, that it's not destroyed, just gets transferred into one form to the next, right? So the universe has a certain amount of set of energy. And so what our body is it just taking stuff in. It's not creating energy out of anywhere. It's taking that Snicker bar, taking the energy from the Snicker bar to basically allow our body to function. And so this is the general reaction mechanism for cellular metabolism. It starts here, that's glucose, plus 6 oxygens go to 6 carbon dioxide, 6 waters, and ATP. And so you know that this is amazing because of 666, right? We all know what that is. And that kind of gives most of people's idea what they feel about cellular respiration. And it was mine as well until I did about 5 years of study in just oxidative phosphorylation, or more so the electron transport chain, which is the reason why I love nutrition and these sections, because it basically goes over everything a lot of what my research was in grad school. And so oxidation, I like to say Leo, the way I remember it, Leo, remember, Leo is the name of our lion here, says Gur. Loss of electrons is oxidation. Gain of electrons is reduction. And you can follow this by following the hydrogens. And so if you look here, you have C6H12O6. And then this guy gets oxidized to carbon dioxide, which do you see how it's just C and O2? Which means we lost the H here. So this is an example of an oxidation reaction. If you look here, you have the oxygen, and basically this oxygen gets reduced into water. And so if you notice, there's no hydrogens here, but we add them here. So that's a reduction reaction. And basically we see these all through cellular metabolism. There are basically 4 series of reactions that take place in the presence of oxygen here. We have glycolysis, we have the intermediate step, which most people don't consider that an actual step. It's like a molecule that you make between here and here. The Krebs cycle and electron transport. And this is the overall reaction. It's glucose, 1 glucose, right? 6 oxygens will turn into or lead to 6 carbon dioxides, 6 waters, and ATP. And we're going to talk about how many ATP as we go through this. And so, yes, metabolism is overwhelming. If you look at this PowerPoint slide, you will see these are all the different metabolic chains that we're talking about. And we are looking at this guy here and this guy along with these guys here. That's about it, guys. Okay? So, but this just gives you a scope of how overwhelming the process of metabolism can be. And so when we're looking at this, you can see we start with the first process, which is glycolysis. And this is where you're going to take your glucose, it's coming from your carbohydrates, and it's going to change it into pyruvic acid or pyruvate. This happens in the cytosol, right? And basically it goes from 1 molecule of glucose to 2 molecules of pyruvic acid. So from this point on, everything is multiplied by 2. Now, this happens out in the cytoplasm over here, or the cytosol, right? And then the rest of the processes are going to be in the mitochondria, so we need to get through here. Now, we're going to make acetylcholine in this, and that is what we know as the intermediate step. And that's important because it's going to feed into the Krebs cycle. The Krebs cycle is also known as the TCA cycle, the tricarboxylic acid cycle. There's a lot of different names that it has. So, this guy is basically, you're going to have 2 molecules of acetylcholine coming in here. And from here, you're going to make all kinds of energy carriers. From each process, from here and from here, we are going to make what's known as NADH. And these are electron carriers. And basically, in the form, they are going to store the chemical energy that's going to move over here to go into what's known as oxidative phosphorylation. And this is a series of what's known as the electron transport chain and chemiosmosis. And through that process, we're going to make the most ATP here. Okay? So we're going to talk about each one of these steps in more detail. So, the very first stage we're going to talk about is glycolysis. And your main reactant that you're going to start with here is glucose and this molecule called NAD+. Now, both of those are important to allow this reaction to happen? Of course, it's in the cytoplasm. And so the products that you're going to make are 2-pyruvate, 2-NADH, and 2 ATPs. Now, if you are making ATPs, then you know that you also need ADP as well, right? And so let's look at all the different molecules and where they're coming from here. And so this is glycolysis. And so as you notice, here is glucose coming in. And if you go through here and you check it out, basically the very first phase that you're looking into from here to here is what's known as energy investment. What does that mean? Do you notice that we have 2 ATPs coming in here? Right? So we have 1 glucose that we start with, and now we have 2 ATPs. The ATP is bringing in energy. And you can see, just so that I can show you, because I just love the biochem of all of this physiology that we get to learn. This is a circle, right? Because carbohydrates can both be in cyclized or linear. And then once this reaction happens, and this is the name of the enzyme, hexokinase, basically you get this really long line here. You can see that the green is here and the blue is here. And then the phosphate that helped with getting some of that energy in is put right there. Then you have phosphoglucose isomerase come in here. And basically, if you look, the only thing they're doing is this end gets changed a little bit. And an isomer is something that has the same molecules but looks differently. Or has the same atoms but looks differently. And then again, we get more energy coming in, and now we have phosphates on both sides. So do you need to know all the particulars of the chemistry? No. But you do need to know that these first 3 enzymes are involved in the energy investment phase. And you start here with 1 glucose and 2 ATPs. Now we get to this area here. That's called the second phase, which is cleavage. And that's exactly what's happening here. Like a meat cleaver, you're going to cut them in half. One is going to go to a molecule called DHAP, and then the other one is G3P. Now, remember earlier when I talked about I just made a mention of the hot stepsister and the ugly stepsister? And so on here, what's happening is this guy, glucose 3-phosphate, this is the hot stepsister. This is the one that's going to keep going out on dates, i.e. we're going to keep going. This right here just happens to be the ugly stepsister. She's not going anywhere. The only way that you're going to get her to go anywhere is if you make her change and you do a makeover into the hot stepsister. Which happens. There's this enzyme here that creates that process. And so at this point, guys, we now have 2 molecules of G3P. Right? We cut them in half, but this guy right here got changed. And so this whole process here happens twice, right? Sorry. And so once we get these 2 molecules of glyceraldehyde 3-phosphate, we're going to move on. Now the reason why I said this is where the glycerol from the fatty acids enters in here. And you can see glyceraldehyde is a way that you can remember that the glycerol part of this is what makes all this work. Now we had 1 glucose, 2 ATPs, and now we're bringing in an NAD+. Now, NAD+ to NADH. Question here. Oxidative or reduction reaction? Leo says GER. Loss of electrons, oxidation, right? Gain of electrons, reduction. So if you notice, we go from being positive to not having a positive sign anymore. To get rid of positive or protons, you add electrons. Now, you can also just remember reduction means you add an H. So this is a reduction reaction. And this is how we're getting some of that energy over. So we're going to have that NADH come in here through this. And so you're going to have basically 2 NADHs, because remember, this happens 2 times. And then this last phase that you see is what's known as energy liberation. And let's see why we call it that. Well, do you see how you have an ADP here, and it comes out and it makes ATP, right? So we're liberating energy. How many are there? Well, that part happens twice. So there's 2 ATPs here, right? Then you go through, you'll see water's released here. And then what's this last step doing? Again, making ATP. So you have 2 ATP molecules here. That's a total of 4, right? So the net outcome of ATP here, if you remember, I said 2 ATPs are made, right? Really 4 total, but we used 2 of them at the beginning. So these are the 3 stages of glycolysis that happens in the cytoplasm or cytosol. So you can see here, phase 1, energy investment. You can see the sugars being activated, and you're going to take 2 ATPs in to make 2 ADPs. Cleavage is when you take that fructose 1,6-bisphosphate and you cleave it in half by aldolase. And this is a cleavage reaction, right? And then you have DHAP, DHAP, which is a dihydroxyacetone phosphate, and glyceraldehyde 3-phosphate. And basically, this guy gets moved to this guy, so you continue to the last phase, which is then energy liberation. You liberate 4 ATPs here, but your net outcome is 2, right? So glycolysis net outcome of ATP production is 2 ATPs. You also make 2 NADHs here, which go on to the last phase, which is oxidative phosphorylation. Now this guy, our final product is 2 pyruvates or pyruvic acid, right? And so this guy can't feed straight into the Krebs cycle. So this is what's called, it's used pyruvate dehydrogenase. Basically comes in and takes with a coenzyme A, changes this up, and makes acetyl-CoA to go into the Krebs cycle. If there's not enough oxygen, this is if oxygen's present. If oxygen isn't present, then the process of fermentation happens. And so what happens is when we make this NADH, and this goes to oxidative phosphorylation, basically when it's done, it makes NAD+, and that can come back here and work with glycolysis. If you have no oxygen, that doesn't happen. And so the process of fermentation is taking those 2 NADHs and putting them into NAD pluses to go back into this. And the process of that makes lactic acid. And that's why if you're out of shape and you go to run, the next day you're really, really sore because you have lactate or lactic acid buildup in your muscles that destroys your muscles. And that's because there's not enough oxygen there to help with this whole process going to fruition. So basically, to make enough glucose to keep running, they go through the process of fermentation.
Hey, sugar, come on over here, sweetie. Let's break it down. Glycolysis is a series of reactions, enzymatic actions, energy transactions. Takes glucose, a molecule so sugary, breaks it down to NADH and ATP. It's an anaerobic cytoplasmic pathway that amazes, organized easily into 3 phases: investment, cleavage, and energy harvest. Tell me later which one you like best. Investment, activation, energy supplied. Cleavage, our 6 carbon sugar divides. Harvest, we get our energy yield. So beautiful, so intricate, keep your eyes peeled. Glycolysis. Come on, sugar, for the breakdown. For the breakdown. Investments, like striking a match. That energy you put in makes the fire catch. For glycolysis, investments, 2 ATPs, which act as activation energy. Enzymes take phosphates from ATPs, jam them on a glucose, rearranging it to fructose, leaving fructose 1,6-bisphosphate on the table with 2 phosphates. It's highly unstable, moving us to the second phase, the cleaving of fructose bisphosphate, because glycolysis means splitting sugar, you can see. Cleavage yields 2 molecules with carbons 3. One is glyceraldehyde 3-phosphate G3P. It continues on our pathway broken down for energy, but the second one, an enzyme, will immediately convert into a second G3P. Glycolysis. Come on, sugar, for the breakdown. For the breakdown. Phase 3, G3P gets rearranged and oxidized by an enzymatic assembly line that harvests energy from each G3P, 1 NADH and 2 ATPs. Double this yield per G3P to 2 NADH and 4 ATPs. That's the gross yield for every glucose in. A generous accounting of glycolysis is win, but 2 ATPs were invested in phase 1, so you net just 2. You can use to jump or run. Put 2 in, get 4 out, your net gain is 2. 2 ATPs that you can use. If that doesn't seem like very much, it's 'cause it ain't. There's tons of energy left in pyruvate. The 2-3 carbon molecules we're left with at the end, and what happens to pyruvate's going to depend on the metabolic pathway where pyruvate gets sent. If it's anaerobic, it'll be fermented, but in aerobic cells, pyruvate's termination will be the Krebs cycle and total oxidation. Glycolysis. Come on, sugar, for the breakdown. For the breakdown. Glycolysis starts with investment of 2 ATPs to the glucose that we started with. The product is cleaved into 2 G3Ps from which the cell harvests NADH and ATPs. This anaerobic pathway is respiration's first phase, billions of years old, evolved in ancient days before O2 accumulated in the seas, before eukaryotic cells arrived on the scene. It's everywhere, ubiquitous in every organism. Bacteria, sequoia tree, no matter your metabolism, happens in the cytoplasm, doesn't need no organelles. You want to find glycolysis? Look at any cell. Glycolysis. Come on, sugar, for the breakdown. For the breakdown. Glycolysis.
So that's my favorite Glen there. So now we're on to this really quick. This is the intermediate phase. You can see here you have the pyruvate, and it comes through these shuttles into what's called the mitochondrial matrix here. Right? This is the inner membrane here. This is the outer membrane. This is the inner membrane space between the two, right? And so here you're going to basically have this pyruvate mixed with an acetyl-CoA derivative and that NAD+. And through pyruvate dehydration is going to make that acetyl-CoA. This is a coenzyme A here. And so that's going to add that coenzyme A onto the pyruvate molecule, making it acetyl-CoA for the coenzyme A. This is the first time you'll see the production of the waste molecule carbon dioxide and our electron carrier NADH. Now, CO2, when you're running, right, you'll start breathing a lot. And the breathing isn't to get oxygen back to your body, it's to get rid of CO2. So this is the first place for which you're starting to make CO2. And then we're going to talk no more here in a second about the second spot. So this is not technically part of the 3, but I like to include it in there. It's a preparatory stage to the Krebs cycle. So the third stage of cellular respiration is known as the Krebs cycle, the citric acid cycle, the TCA cycle, or the tricarboxylic acid cycle. They're all used. It happens in the mitochondrial matrix, the same area, and basically this is where the complete oxidation of glucose occurs. So basically all the electrons that we can take from glucose and break it down, this is where we're happening. Again, our major starting product or reactant is 2-acetyl-CoAs, right? And these are all the guys you're going to make. You're going to make 4-carbon dioxide. Total waste product, right? This, NADH, is going to go to the oxphos. FADH2, this is the first time you've seen it. This is in another electron carrier. It's going to go to oxphos. And then 2 ATPs are made here. So if you go into this, right, you can see basically what happens is that transitional or intermediate phase that goes from the pyruvate or pyruvic acid to acetyl-CoA. And then basically what happens is acetyl-CoA comes in, combines with oxonyl acetate, which is part of the cycle, and makes citric acid immediately. That's the initial molecule that you react with. Thus the reason why it's called the citric acid cycle. And then from there you can see it's cyclic, it goes around. And so here is one NADH you make, here is one ADH, and here is one NADH. Now you only see 3 there, but remember how many times does this happen? Twice, because you have 2 pyruvates because we've cut the glucose molecule in half. Again, you have one FADH here. That means you make 2. And then you can see you have one ATP here. Again, you make 2 because this is 2 cycles around.
Matrix of the mitochondria of all our cells is the cycle of reactions that were Hans Krebs a Nobel Prize. The cycle takes the energy in food and makes it into other forms your cells can use. Krebs cycle makes electron carrier NADH, which later brings electrons to the electron transport chain. And Krebs makes FADH2, its function is the same. Krebs also makes some ATP, another claim to fame. We're talking Krebs. It's a citric acid cycle, Krebs. Tricarboxylic acid cycle, Krebs. Each cycle makes 1 ATP, 3 NADH, 1 FADH2. Right before the cycle's a transitional part, links Krebs to glycolysis so Krebs can start. Enzymes rake a CO2 off a pyruvate, yields an NADH and acetyl-CoA. Acetyl-CoA carries carbons too, with all the energy that derives from food. It's a highly reduced molecule with energized electrons that fuels up the Krebs cycle as it cycles on. Now at the start of Krebs, this acetyl-CoA has the 2 carbons it carries in, ripped away. Enzymes put these on oxaloacetate with carbons 4, make 6 carbon citric acid. Who could ask for more? Notice 3 carboxyl groups on the citric acid. That's why the cycle's also named for tricarboxylic acid, or TCA cycle if it's acronyms that you prefer. Krebs in honor of its discoverer, Krebs. It's a citric acid cycle, Krebs. Tricarboxylic acid cycle, Krebs. Each cycle makes 1 ATP, 3 NADH, 1 FADH2. Enzymes work on citric acid and remove the CO2, and other enzymes modify and oxidize it too. The 5-carbon result is alpha-ketoglutarate. Krebs cycle, it's so great. Every oxidation can power the reduction of NAD+, which gains electron carrying function, become an NADH, that energy sensation, which later on in respiration powers ATP creation. Another oxidation follows another CO2 remove, leaving us with a 4-carbon molecule. Another NADH results from this oxidation, as Krebs does its energy transformations. This 4-carbon molecule, acetyl-CoA, still has lots of energy enzymes can take away. A series of reactions yield 1 ATP, the cell's main energy currency, leaving just enough energy for enzymes to reduce NFADH to FADH2, and 1 last NAD+ will also get reduced as the final electron carrier NADH gets produced. We've harvested what energy came in at Krebs' start. Now we have oxaloacetate at this final part. Oxaloacetate is the commencement and finale, ready to meet acetyl-CoA, and here at the final tally. Krebs goes round and round, such an ancient cycle, spinning like the wheels of my bicycle. Krebs like the axle of aerobic respiration. I breathe out CO2 with every exhalation. We've walked through the cycle, so now let's review. Input is acetyl-CoA, but the carbons too. The carbons get removed, releasing CO2. Exhaling sends the CO2 out of you. The cycle's functions: energy transformation, 3 NAD, H1 FAD, H2 creation, and also synthesis of 1 ATP, which cells directly utilize for energy. For every glucose cells absorbed, the cycle runs 2 times. As long as cells get fuel, Krebs is running just fine. It precedes electron transport chain, it follows glycolysis, and spinning round and round in the mitochondrial matrix. Krebs. It's a citric acid cycle, Krebs. Tricarboxylic acid cycle, Krebs. Each cycle makes 1 ATP, 3 NAD, H1 FAD, H2, Krebs. It's a citric acid.
I do really like those songs. Anyway, so now let's look at the final part, oxidative phosphorylation. And so what we're going to have here, it's made up of 2 parts. It's part of the electron transport chain, which is a set of enzymes that basically are going to pump hydrogens across the membrane to create a gradient to do the last part, which is chemiosmosis, activate ATP synthase. And so the location that this happens is in the area called the cristae, which are these invaginations in the mitochondria in the intermembrane space. Electrons are carried in, or that energy of the electrons are carried in by NADH and FADH2. The NADH is coming from both the Krebs cycle and glycolysis, along with that intermediate step that we talked about, and the FADH2 is coming in from the Krebs cycle. They are going to be passed through a series, so they're going to donate their electrons to an enzyme, and then those enzymes are going to pass them down through a series of electron-carrying reactions. The electrons move from high energy to low energy. It's almost like they're going down a slide from the top to the bottom. And once they're at the bottom, or you can say that they're dropped off on a big mountain at the top by a helicopter, and they're just going to roll downhill, and when they get to the very bottom of the hill, they need to go somewhere, so a boat's going to pick them up, right? And so you're going to see this go through here. Energy from the electron pump that you basically pump these protons or hydrogens across from the matrix to the intermembrane space is going to help activate ATP synthase. So it yields up to 30 to 34 ATP molecules per glucose molecule. So
in the mitochondrion, the energy stored in NADH is used to generate a proton gradient across the mitochondrial membrane, and the energy of the proton gradient is used to make ATP. When glucose is oxidized during glycolysis and the Krebs cycle, the coenzymes NAD and FAD are reduced to NADH and FADH2. Inside the mitochondrial matrix, the electrons from NADH are transferred to the electron carrier coenzyme Q by NADH dehydrogenase, and the protons are transferred across the membrane to the intermembrane space. Coenzyme Q carries the electrons to the cytochrome BC1 complex. As the electrons move from the BC1 to cytochrome C, more protons are carried from the inside to the outside of the membrane. Electrons are also transferred from FADH2 to coenzyme Q, with the protons being transferred across the membrane. Cytochrome C transfers electrons to the cytochrome C oxidase complex. Protons are also transferred to the outside of the membrane by the cytochrome C oxidase complex. The cytochrome oxidase complex then transfers electrons from cytochrome C to oxygen, the terminal electron acceptor, and water is formed as the product. The transfer of protons to the intermembrane space generates a proton motive force across the inner membrane of the mitochondrion. Since membranes are impermeable to ions, the protons that re-enter the matrix pass through special proton channel proteins called ATP synthase. The energy derived from the movement of these protons is used to synthesize ATP from ADP and phosphate. Formation of ATP by this mechanism is referred to as oxidative phosphorylation.
So that kind of gives you a good idea on how it works. So what you have these series of enzymes, right? And so for simplicity, they call them enzyme or complex 1, complex 2, complex 3, complex 4. They do have tougher names. For instance, complex 1 is NADH dehydrogenase, complex 2, succinate dehydrogenase. So for simplicity, though, we'll call them by their complex name. And so basically, complex 1 here will take in NADH, which is the electron carrier. They take the electrons in and they'll pass them through. You'll see there's this shuttle, coenzyme Q, that moves it from this enzyme to 3. So 1 goes to 3. And as you move these through, it's going to use the energy to pump hydrogens from the matrix here to the intermembrane space. Now, once it gets through 3, it's going to hop onto cytochrome C and then go to 4. Then again, you'll see as it moves through, it's going to use that energy to pump the hydrogens across. And then the boat it dumps on is oxygen. So you take oxygen and you make metabolic water. So when we're talking about basically electrolyte balance and fluid balance, when we talked about making metabolic water, this is one part of it, right? And so once we get all the hydrogens built up here, you're going to get all these positive charges here. And basically that's going to act kind of like a water wheel or water to a water wheel here. And it's going to allow hydrogens to go through here. That's going to activate ATP synthase to start rotating around. As this kind of broccoli piece down there opens or rotates around, basically what happens is these areas right here open, bringing ADP and inorganic phosphate into that site, and then they close to bring them together, and that is what makes ATP. So this part's called the electron transport chain. This part is called chemiosmosis because you're taking chemical and osmosis together. You're moving chemicals, aka hydrogens or known as protons, down a chemical gradient. And you're using that gradient to activate ATP synthase. Again, you can just look at this and see the most important components on there. You do get that electron transport chain, helps to create that proton gradient or hydrogen gradient to allow activation of ATP synthase. NADH comes into complex 1, FADH2 comes into complex 2. They both are going to donate their electrons to complex 1 for NADH, complex 2 for FADH2. Now, if it goes through complex 1, it's going to pump proton gradient, or it's going to allow the protons to go through the channel. Now, if you notice, complex 2 does not. This is almost like having two doors in your house, a front door and a back door. If it goes through 1, it goes from 1 to 3. It goes from 2 to 3. 2 and 1 never interact with each other. 3 and 4, again, as the electrons are moving through them, you're pumping hydrogens, and then you have these shuttles between the enzymes, Q and cytochrome C. Cytochrome C is also important because if something happens to the mitochondria and it gets released out of the mitochondria, that is one of the signaling mechanisms to start apoptosis or programmed cell death. This guy, the electron transport chain, is actually pretty interesting. For instance, if you want to kill someone and you do cyanide, it actually binds to what's known as cytochrome oxidase. Cytochrome oxidase is complex 4 here. So really, technically, right, you're making it so cyanide is binding where oxygen normally would bind. And this is irreversible. So this is how cyanide works to kill people. There's also something known as dinitrophenol or DNP. In the underground sections of like weight loss and exercise, they use this. And it was used really commonly back in the 70s. It was actually stopped by the Food and Drug Administration because it was an amazing weight loss drug. It still is. It's absolutely fantastic. And you can still buy it, like I said, on the underground from the same people that you can buy things like steroids from, right? And what it does is dinitrophenol or DMP actually puts kind of like the max do. They put holes or channels within the membrane. And so they pump these places, and then instead of hydrogens coming out to make ATP, they'll just come back through. And then they basically, electron has to keep breaking down food and keep doing this, but you're never making any ATP. So the problem with this is it generates, because it's not really working to transfer this energy from glucose into ATP or anything else. The problem with this is that A, if you take too much, you can kill yourself because the mitochondria can no longer make any ATP because it can't generate this gradient. And B, if you take too much as well, because you have all this energy being converted, it has nowhere to go and be used, it causes your temperature to raise drastically. And there's no way to get it down at a certain point. It just keeps getting higher and higher and higher and higher. And before people realize it, they're denaturing all their proteins and they're dying. And this is what was happening to the people in the 70s, that they were taking too much of this and basically they were burning themselves out, right? And it basically, from what I've read, because obviously I've never taken it, never would, people feel like they're burning from the inside out. So if anybody ever, and it can also cause, if it doesn't kill you there, it can cause skin lesions and it can cause cataracts. And basically it just completely uncouples electron transport to ATP synthase. And it can basically change your temperature. A lot of times an average 38 degrees Celsius. Some people can be as high as 43 degrees Celsius. Or it can, 38 degrees Celsius is the average, and this can change your temperature up to being about 43.3% Celsius on average. That's 109 degrees, guys, right? And so, yes, it can very much kill you. So these are just a couple things that relate specifically to the electron transport that you may come encounter if you're ever a healthcare professional. And so the average that we make in this, just remember, it's the highest amount of energy that's made out of every process here. And so this kind of gives you an idea, and it changes, right? This says 28, but I would look at 30 to 34 is the average, and it's, on average, you're looking at 36 to 38 ATPs. Every book, it's a little bit different, right? And so this kind of gives you a review on everything and how everything's going. And at this point, I'm not going to kill a dead dog anymore. So I'm going to show you this quick video. And then we're going to talk about some other pathways that happen.
As this mountain biker heads up the trail, the breakfast he ate this morning is being burned to power his bike ride. His breathing rate increases as his leg muscles demand more oxygen to burn more fuel. Let's zoom down to where this fuel is burned, our cells. Here, the blood vessel on the left delivers fuel and oxygen to a single muscle cell. In cellular respiration, energy in fuel is converted to ATP, shown here as starbursts. Most ATP is made in the cell's mitochondria. ATP powers the work of the cell, such as contraction. Let's take a closer look at how ATP is produced from a molecule of glucose, our fuel. Only the carbon skeleton is shown to keep things simple. The first step is called glycolysis, and it takes place outside the mitochondria. To begin the process, some energy has to be invested. Next, the molecule is split in half. Now, the molecule NAD+, an electron carrier, picks up electrons and hydrogen atoms from the carbon molecule, becoming NADH. Keep track of the electron carriers. They play an important role by transporting electrons to reactions in the mitochondria. In the final steps of glycolysis, some ATP is produced, but not much. For every glucose molecule, only 2 net ATPs are produced outside the mitochondrion. However, glycolysis has produced pyruvic acid, which still has a lot of energy available. Let's follow this pyruvic acid molecule into a mitochondrion to see where most of the energy is extracted. As the molecule enters the mitochondrion, 1 carbon is removed, forming carbon dioxide as a byproduct. Electrons are stripped, forming NADH. Coenzyme A attaches to the 2-carbon fragment, forming acetyl-CoA. Coenzyme A is removed, and the remaining 2-carbon skeleton is attached to an existing 4-carbon molecule that serves as the starting point for the citric acid cycle. The new 6-carbon chain is partially broken down, releasing carbon dioxide. Several electrons are captured by electron carriers, and more carbon dioxide is released. The carbon dioxide that you exhale comes from the reactions of cellular respiration. 2 ATPs are produced by the citric acid cycle for each molecule of glucose. At this point, only a small number of ATPs have been produced. However, more energy is available in the electrons that are being transported by electron carriers. While the citric acid cycle starts another round, let's follow an electron carrier to the next step in the process. Electron carriers such as NADH deliver their electrons to an electron transport chain embedded in the inner membrane of the mitochondrion. The chain consists of a series of electron carriers, most of which are proteins that exist in large complexes. Electrons are transferred from one electron carrier to the next in the electron transport chain. Let's take a closer look at the path electrons take through the chain. As electrons move along each step of the chain, they give up a bit of energy. The oxygen you breathe pulls electrons from the transport chain, and water is formed as a byproduct. The energy released by electrons is used to pump hydrogen ions, the blue balls, across the inner membrane of the mitochondrion, creating an area of high hydrogen ion concentration. Hydrogen ions flow back across the membrane through a turbine. Much like water through a dam, the flow of hydrogen ions spins the turbine, which activates the production of ATP. These spinning turbines in your cells produce most of the ATP that is generated from the food you eat. The process you've just observed, cellular respiration, generates 10 million ATPs per second in just one cell. That ATP can power a biker up the trail, or it can power your brain cells as you learn challenging biology topics.
And so we talked about basically where we get the major macromolecules that we can utilize for making energy, specifically making or storing energy in the form of adenosine triphosphate or ATP, and then using that later. And so the first question is, where does glucose come from in order to start glycolysis? And that comes from basically two. Of course, it may come from essentially eating different forms of, or eating carbohydrates, glucose specifically. But it can also come from essentially body stores. And so there's two major processes in our body. There's one that's called glycogenolysis. And gluconeogenesis. Glycogenolysis is basically the process of breaking down stored glycogen into glucose. that basically goes into glucose, right? So glycogen is basically if you eat food and then you have this extra leftover amount of glucose going around in your bloodstream, then your body will trigger to store it for later. And it goes into this basically process of taking glucose and putting it into a molecule called glycogen. And that process is what's called gluconeogenesis, right? And once you basically go some time without having any glucose or lower levels of glucose in your blood, then it'll start breaking it down. So it uses these two processes to make sure that you always have an available source of glucose in your body. Glucose as well. Now, we don't just eat carbohydrates, we also use fat. And so fat can be, yes, used to basically make ATP. And so the process of breaking down fat is what's known as lipolysis. And it's done by lipases. And basically what it does is it forms what's known as glycerol and fatty acids. Those are the two structural components of a triglyceride. Now, fatty acids can be further broken down into acetyl-CoA. And if you remember, acetyl-CoA is the pre-molecule that goes into the citric acid cycle, or the Krebs cycle, right? And the process of taking these fatty acids and breaking them down into acetyl-CoA is a process known as beta oxidation. We're going to go into this more and actually look at some of these pictures more later. And the last thing is, can proteins be utilized for cellular respiration? And hopefully, again, you realize the answer is yes. And it can be broken down into a lot of different things. For the most part, you can see them being broken down into acetyl-CoA again. Now, this process is known as deamination. And basically what it does is it removes, and deamination is basically talking about removing what are known as amine groups. And this is what an NH2 is, what an amine group looks like. And so you can break down proteins to feed straight into the Krebs cycle, and then a deamination is going to produce basically byproducts, because then that amine group is changed in the body or processed to NH3, which is ammonia. And then this gets further processed into this crazy looking molecule here. And this is what's known as urea, right? And then you'll get rid of it. So during normal bouts where there's plenty enough of food to go around for everybody, there's no problems. But in cases of things like starvation, it can be a problem, right? And basically, your body prefers glucose. It's the easiest to break down for the optimal amount of energy. And it requires the least amount of energy to make energy from cellular metabolism, because you're not having to break other molecules down and convert them, a process of catabolism and anabolism together to create these molecules that feed into cellular respiration, which is what you're having to do when you take things like fats or proteins. So to kind of look at some of these things again, here's when we're talking about where does glucose come from in order to start glycolysis in the cell. And so you can see the two major aspects here is glycogenesis and glycogenolysis. And so basically, when we're looking at here, you can see here you have a lot of blood glucose. And so you are going to basically synthesize glycogen here. And so glucogenesis here, basically you take these small molecules of glucose. This, of course, is you have more glucose there than you need the need for ATP. So basically, you have, if you look at glycolysis, the very first basic enzyme, one of the very first enzymes is hexokinase. And so through here, you make glucose 6-phosphate, which if you remember, that's a process. There's several steps here, right? That makes the hot stepsister. Well, instead of continuing throughout, you'll see that it changes a little bit into glucose 1-phosphate. And then from here, using the enzyme glycogen synthase, you're making the storage molecule. Now, glucogenolysis, and you can see lysis here, genesis as in building or creation, right? Lysis as breaking down. You can see you have low blood sugar here. And so you have these stores of glycogen. So this enzyme called glycogen phosphorylase is going to start breaking it down into the opposite direction. And basically you have this enzyme, glucose 6-phosphatase. You can see it's present in the liver, kidney, and intestinal cells that are going to help break it down even further and release those individual glucose. So this is how you're basically regulating blood sugar and cellular respiration in the body to allow it to continue. And so on here, glucolysis is basically, or glycolysis, right, is what you do for ATP. These are a quick summary of what happens. Glucogenesis is a process when you're basically taking glucose, when you have excess amount of glucose and you don't need to use all the ATP to make the storage. Glucogenolysis is when you're taking the glycogen store and making it so that you can release sugar when sugar is less. And gluconeogenesis is basically making glucose from non-carbohydrate sources. This takes a lot of energy to do. And so this is going to talk a little bit about what happens during starvation.
Medically speaking, starvation occurs when a body doesn't get enough calories and nutrients, whether brought on by poverty, famine, being lost at sea, voluntary hunger strikes, or medical conditions. The physiology of starvation follows the same process no matter the cause. And it really is a process. It takes time to starve to death. Without oxygen, our bodies shut down in 5 or 10 minutes. Without water, we can last maybe a couple days, a week at most. But depending on the circumstances, a person might go as long as 2 months without any food at all. During this time, the body passes through 3 distinct metabolic phases as it desperately tries to stay alive until it finds food again. Phase 1 is where your body picks the lowest hanging fruit, energy-wise, through glucose burning. In your normal, well-fed state, your body breaks down glycogen molecules to produce glucose, the friendly carbohydrate that keeps your cells well-fed and functioning. The average person can typically go about 6 hours after feeding in the glucose-burning phase before they start feeling hungry and probably grumpy. At that point, your body has burned through all that lunchtime glucose and is turning turning toward fatty acids, the building blocks of fat molecules stored in your tissues, to fuel itself. This switch kicks off the first big metabolic shift as your body enters phase 2 of starvation, fat burning. The fat burning phase can last from days to weeks. During this stage, called ketosis, our livers metabolize fatty acids into smaller fat chain derivatives called ketone bodies. They replace glucose as the main energy source. These compounds come in 3 different water-soluble configurations that move from the liver to the heart, brain, and other tissues during periods of fasting to try to keep things going. Some people, like hard-training triathletes or bodybuilders or those on a super low-carb, high-protein diet, may be in ketosis pretty often. It doesn't mean they're starving, it just means that their bodies are running differently because either they're not eating enough carbs from which to get glucose, or they're quickly burning through them. But if you're thinking that eating butter-covered bacon to burn body fat sounds like a good deal, you should know your brain might be less than amused. Your brain can't directly use those fatty acids as fuel because they're too big to squeeze through the blood-brain barrier. And our brains are a big energy suck. They demand about 25% of our stored energy to function properly. They're kind of greedy like that, needing about 120 grams of glucose a day to stay happy. That's like 3 cans of Coke. It's like 4 cans of Coke if one of them's diet. So in your first day or two without food, while the rest of your body starts fueling itself on fatty acids, the brain drains the last bit of stored glucose until it really runs out. But you probably noticed that no one dies after just 2 days without food. That wouldn't make very much evolutionary sense. Luckily, your brain is smart and it has a backup plan. Within a few days of no food, your brain recalibrates its glucose requirement from 120 grams to about 30 grams, and it changes the menu. The brain now starts eating those processed ketone bodies, which, because they're smaller than fatty acids, can get through the blood-brain barrier. This is a great evolutionary trick to keep us alert enough, no matter how hungry we are, to continue to look for food. But even if you are semi-alert, you're definitely not in a good mood. As a hungry brain is continually deprived of vital nutrient, it gets to feeling depressed, anxious, lethargic, and socially withdrawn, and starts to have trouble concentrating and comprehending. The third and final phase of starvation begins when all your fat stores are burned up and the body switches to using its final reserves, proteins. This phase is marked by rapid muscle depletion as your body cells start to break down their own proteins into amino acids, which your brain now gobbles up. Proteins are essential for proper cell functioning, so things go downhill pretty quickly as your body starts eating itself, basically, in a process of internal self-cannibalism called catabolysis. Still, your ever-optimistic body tries to run damage control by eating up your least vital cells for as long as possible, as it holds out hope for more food. But after weeks of no food, once your body has burned through all available glucose, fatty acids, and protein muscle mass, it's got nowhere left to look, and the end is near. Keep in mind that by this point, your body is so grossly deficient in vitamins and minerals and has such a weakened immune system that just about anything could kill you. In the end, the ultimate cause of death during starvation is often cardiac arrest due to excessive tissue degradation. The heart simply can no longer support itself with such limited resources. It's enough to make us all, I hope, really appreciate everything we eat, at least for this one day. Thank you for watching this episode of SciShow. If you have any questions or comments or ideas for us, we're in the comments and on Facebook and Twitter.
Okay, so that should give you a bit of an idea of how starvation works. And so basically there are 3 stages of metabolism of energy-containing nutrients, right? So stage 1 is the actual digestion in the GI tract, lumen. And at this point, they're going to absorb these different forms as, i.e., proteins, carbohydrates, and fats. And they're going to transport them via blood to tissue cells. So as you can see, for the protein, basically we're going to utilize the amino acids from them. From carbohydrates, there's glucose and several other sugars that we're going to get from that. And then, of course, the most commonly form of lipids that we have are triglycerides, and they are going to divide into glycerol and fatty acids. From here, we go into stage 2, and this is basically when you have both the process of anabolism and catabolism happening. And what do I mean by this? I say, well, if you look over in this area that says proteins or amino acids, basically, they're not just going to automatically make these molecules when we're talking about amino acids being there. What they're going to do is they are going to have to change their form of monomer, you can see, to make it into an acceptable molecule that glycolysis or cellular respiration in general can utilize. And so you can see on most of these that you're getting an amine group leaving. This is in the form of ammonia. And you can say it can go into glycolysis, the precursor to the Krebs cycle is acetylcholine, and the less frequent being going in directly into the Krebs cycle. Of course, here with glucose, you can either go into the storage molecule for glycogen, or you can basically see that it is breaking into glycerol, going into glycolysis, specifically being glycerol 6 or G3P, glycerol 3, aka the hot stepsister. And the fatty acid is actually going and changing and becoming acetyl-CoA. And then they'll go through. And the last stage of this is oxidative breakdown. And so basically, at this point, most everything has gone into some other stage, except at some point, sometimes infrequently, proteins or amino acids can go into the Krebs cycle. And this is a process that you start making ATP through essentially reactions. So you can see at some of these that the anabolic reactions are happening when you're actually making glycogen stores or proteins or fats coming together. And essentially most of the catabolism happens when you're starting to break down these to actually form these molecules that go into the cellular respiration. And so let's focus on lipid metabolism. Lipids actually provide a greater energy yield than from glucose or protein catabolism. And essentially on here, fat catabolism yields about 9 kcals per gram. If you're looking at carbohydrates or proteins, it's normally about 4, so you're getting almost double the amount of energy here. And this is something that's not new. We know that you can get a lot of calories from fat. If you try to eat a lot of fat, then you're going to take in more calories. It's transported in lymph as the chylomicrons, right? It doesn't get absorbed straight into the bloodstream. It's too big. So it has to go through the lymphatic system. It's actually hydrolyzed by endothelial enzyme into, as we know, fatty acid and glycerol. And it's done by an enzyme called lipase. So you can see there that it's breaking down. The glycerol will go into glyceraldehyde 3-phosphate, which is a glycolysis intermediate. That's the one that happens after aldolase breaks glucose in half into the 2 different 3-carbon entities. And then it can be further processed through glycolysis to pyruvic acid and mediate through the cellular respiration. Now on here, you're going into where it's only half of glucose, right? It's only this one molecule. Remember when we talked about glycolysis earlier that we had it broke in half too with aldolase. So this is only showing you, or it's only going to produce about half the amount of ATP that a full molecule of glucose would, because it's only one side of it. So this yields about 15 ATPs per glycerol. So it's about half. Now the fatty acids, as you can see, goes in, and you can see coenzyme Q along with ATP water. It's going to make these 2 coenzymes, right? In the process of feeding it into acetyl-CoA. And these guys later will go to oxidative phosphorylation. This process is known as beta oxidation. And basically, this acetyl group that we're going to make binds with this coenzyme A to form acetyl-CoA, which then can enter the citric acid cycle. right? And basically it's referred to beta because it takes off 2 carbons are broken off of this chain. And so this is the process of basically lipid metabolism. So when we're looking, you can take either adipose stores of fat or dietary fat, and we're going to get triglycerides from them. So you have lipolysis, right? Lipolysis is the breakdown of stored fat into glycerol and fatty acids. It's the reverse of what's known as lipogenesis, which is when we synthesize triglycerides. Which, if you go over here, if you basically, if you look, we have lipogenesis here, and this is when we can actually synthesize triglycerides, and that occurs when cellular ATP and glucose levels are high. Why it keeps doing this? Sorry guys for that little guy that's up there. I'm going to have to fix that here in a second. So when you have high glucose levels, lipogenesis will happen. So dietary glycerol and these fatty acids are not needed for energy. If they're not needed, they are stored as triglycerides. 50% is stored in adipose tissue. The other 50% is deposited in other areas. So basically, if we need to, we can take these and feed them into glycerol. Now, if we want to make energy, or if we need to, right, then your fatty acids can be, glycerol can be fed into here into glyceraldehyde 3-phosphate, which I talked about earlier. Fatty acids get broken down to acetyl-CoA through beta oxidation. Now, beta oxidation happens in the mitochondria. And we talked about this a second. It's when your fatty acids are broken down into these 2 carbon acidic acid fragments. And in this process, we're going to make those electron carriers that will feed into cellular electron transport, right? And that's both the Na, we're going to end up making NADH and FADH2 through this process as well. And then basically what happens from here, it's going to feed into the citric acid cycle. Now the problem with this is, in order for the citric acid cycle, if you remember, it feeds into there and it needs an intermediate to basically combine with, right? Over here, called oxonyl acetate. If there's not enough oxonyl acetate there to combine with, to continue around and make energy, then that acetyl-CoA can accumulate. And basically, as this accumulates, the liver is going to trigger ketogenesis. And that's going to make what we know as ketone bodies. And so example of this is acetoacetate or acetoacetic acid, beta hydroxybutyrate, or beta hydroxybutyric acid, and most common that you guys will know is acetone. And so accumulation of these ketone bodies in the blood can be bad. It can lead to ketosis, which a lot of people are striving for all the time, right? Ketosis is basically pretty common in starvation, unwise dieting, or in diabetes mellitus. Ketone bodies are excreted in the urine, so a lot of times if you're on these diets that promote ketosis, you can test it using urinalysis strips. Now, why this can be bad and why when you're using these diets you don't want to stay in ketosis is that ketones are extremely acidic, so the buildup of these molecules can actually lead to metabolic acidosis, which if you've taken my class in part 1, you already know that this can cause the pH levels of the blood to become dangerously low. A lot of times you can figure that someone is in, a patient has ketoacidosis by also smelling their breath. It's very, can smell fruity, and that's from vaporizing the acetone that's in your body. It's trying to get rid of it in some way. Breathing becomes rapid also as lungs try to release CO2 because, as you know from acid-base balance, which we're going to talk about in this next section again, that releasing CO2 can help to reduce the acidity of the blood. Carbon dioxide mixed with water creates carbonic acid, and carbonic acid is an acid, so it'll reduce the pH. So this is one thing. If you have metabolic acidosis, this is created from these ketone bodies, and your body tries to use their respiratory system to get rid of it. Now, lipids can actually also help to make structural material. So, lipids are also important in phospholipids, which help to create cell membranes in the myelin of nerves. Cholesterol is used for cell membranes and steroid hormone synthesis, which is also considered a lipid. And you can see here that essentially you can make cholesterol from here. And basically we synthesize cholesterol from acetyl-CoA. And in addition to making steroids from cholesterol, which cholesterol looks a lot similar to things like testosterone and estrogen, you can also, cholesterol is used to form biosalts as well. So structural material is very, very important as well. And this is just kind of breaking down the process of beta oxidation converts fatty acids to acetyl-CoA. Lipolysis is breaking down lipids to fatty acids and glycerol. And lipogenesis is when you form lipids from acetyl-CoA and glyceraldehyde 3-phosphate. And so this last part we're going to talk about is protein metabolism. And proteins are deteriorated, so they need to be continuously broken down and replaced. Amino acids are thus recycled into new proteins and different components. Proteins are not stored in the body. When their dietary proteins are in excess, basically amino acids are either oxidized to energy, which is what we've been talking about, or converted to fat. So really the goal here is to produce molecules that can be used for energy. In the citric acid cycle, or converted to glucose. How they do this is the process known as deamination. And basically, amine groups are removed and then converted to pyruvic acid or one of the ketone acid intermediates that you see in the citric acid cycle. So let's look at this really quick. So there are three main events of amino acid degradation. Right, number one is transamination. And so basically here, many amino acids can transfer their amine group to basically what's known as an alpha ketoglutarate acid. And then basically it transfers that into what's known as glutamic acid. And so basically a lot of these original amino acids that we have here get changed into a keto acid. And so basically what's going to happen with this guy is that you can see once this amino acid and this keto acid combine together, the keto acid can be modified to fit into the TCA cycle, right? And then you're going to go in this other part of this reaction, the amino acid in form of the glutamic acid or result ends up going through this oxidative deamination here. And so you're going to remove part of the amine group, right, from here. And then you have the ammonia, and this happens in the liver, and then that's going to be converted and combined with CO2 to form urea, and then that's going to be basically excreted. And the keto acid that becomes modified, this is the third one, right? It's going to basically turn into a metabolite that can easily enter the citric acid cycle. So the major metabolites that are produced here in this keto modification are things like pyruvate or pyruvic acid, acetyl-CoA, alpha glutaric acid, and oxonal acetate acid. Now, just to let you know, glycolysis is reversible. So this means that any of the things like pyruvic acid metabolites that are formed could be converted back to glucose. And so this can contribute to the gluconeogenesis. So let's see, this guy here could go back to, it's reverse, so it could go back to glucose, right? So this is what would lead to gluconeogenesis. Remember, and that was a process of making glucose from other entities besides a carbohydrate. So transamination is just transfer an amine group, and that's going to be from an amino acid to the alpha ketoglutarate acid, generating glutamic acid. And then from there, you're going to get the Oxidative deamination, which is removing the amine group, and so this is going to go off as ammonia and basically combined with carbon dioxide to form urea and water, and it's going to leave, right? It's excreted in urine. And basically the urea cycle helps to rid the body of toxic ammonia. That's this process. And this happens from glutamic acid. That is going to be what helps essentially regenerate the alpha ketogluaric acid for transamination to continue. And then from transamination, you'll get the keto acid modification to help produce the metabolites that are necessary for the citric acid cycle. Let's talk about the catabolic anabolic steady state. Now, the catabolic anabolic steady state is a dynamic state, which means this is something that's not going to be, even though it's called steady state, it's not going to be without change. And basically, it's when you're talking about organic molecules, everything but DNA, so protein, carbohydrates, lipids, this is a state that they're consistently and continuously being broken down and rebuilt. And basically, the body uses what's known as nutrient pools. And these pools are just stores of amino acids and carbohydrates and fats, so that we can help to mediate this dynamic steady state. These pools are interconvertible because the pathways are linked, and the pathways are linked by common intermediates. And these are the molecules that basically are between two types of molecules, so it can go one way or another, right? The amount and the direction of conversion are directed by the lipid, the liver, the adipose tissues, and the skeletal muscles. And so interconversion of carbohydrates, fats, and proteins, you can see kind of here where, and we looked at some of this a little bit earlier, right? Basically, as we go through this, a lot of times carbohydrates and fats get linked together. And the reason why you'll hear a lot of them being linked together, why proteins are kind of out by themselves, are because both of these can be stored. So as we talked about earlier, right, you could store carbohydrates as glycogen. You can store fat, right? And both of these, if you look at this, these are both oxidized directly. And so they're treated a lot differently than proteins, right? We don't store proteins for later. We replace them by eating our diet. And we essentially lose proteins. The amino acid pool, basically the total amount of amino acids that are free, are lost, can be lost. Proteins are lost in urine, as you can see here. They're lost in the hair and the skin cells. And these pool of amino acids are important because essentially from here, not only do we form this whole gluconeogenesis here, right? This is the process of being able to make glucose out of other types of molecules. Remember, this is reversible, so it can go backwards into making glucose. They're important because they help to resynthesize body proteins, these amino acids, and then on top of that, they form all kinds of derivatives. You can go further into the citric acid far down here, right? And so these are how these guys change a little bit, and you can see kind of how they fit together. You can see, for instance, the glyceraldehyde 3-phosphate can be basically made or generated through glycolysis and carbohydrates from glucose, right? From basically the breakdown of fats, specifically triglycerides, into glycerol, and glycerol can be generated into glyceraldehyde 3-phosphate, or from that transamination that happens with keto acids. So that guy basically is generated from all three types of main biomolecules. So he's pretty important. But you can see how they're all kind of interconverted here. And so basically, the fed state, it lasts for about, it's all over the place. Here we go. About 4 hours after eating. When absorption of the nutrients is basically occurring. And so anabolism actually exceeds catabolism here. And the excess nutrients are stored as fat if they're not used. So basically, just a reminder that glucose is the major energy fuel. It can be converted to both glycogen or fat. And this happens in the liver. Now, glycogen can remain in the liver, but if there's excess stores, it can move to the muscle, and that's in the form of glycogen, or to adipose tissue, which means it would be converted into fat. Now, fat will leave. It gets released into the blood, and it's going to combine with a protein. And so essentially, it's going to make what's known as a very low density protein. Very low density lipoprotein. And this allows for storage by adipose cells. So this is kind of what happens with glucose directly in the absorbed or the fed state. So when we're looking at the major events and principal metabolic pathways of the absorbed state, you can start here looking at the major metabolic thrust, and when you have anabolism and energy stores. So all of these, if you look, you have these different nutrient pools here. And then, amino acids can then be used for generating proteins. Glucose can be basically excess glucose to form glycogen stores, and glycerol and fatty acids can be used to basically form triglycerides and fat later to store. Remember, these guys, interconversion can happen. And it happens in the liver, in the adipose tissue, and skeletal muscle. Now, the major fuel again is glucose, and it forms our energy intermediate known as adenosine triphase or ATP. It does make, during that course, waste products such as carbon dioxide and water. And during this time, you will have liver metabolism. And so during this, you'll have amino acids that get deaminated. And remember, that's a removal of an amine group and used for energy or stored as fat. So amino acids can go through transamination into ketone acids, and they can be transferred into either triglycerides that can then be stored as fat, and then or used as energy here. And if you look, you can look in certain muscles what's happening during this absorption stage. And so you eat food, it goes through and gets digested, and then in your gastrointestinal tract, it can be absorbed either directly into the blood or through the lymphatic system, specifically the chylomicrons from lymph are hydrolyzed or absorbed when we're talking about triglycerides. So when glucose comes in all tissue, it can be oxidized into ATP or energy. Now, when we're talking about, so that's in all tissues. Now, if we take glucose in muscles, it can be stored as glycogen for later. Now, you can, when you were talking about proteins, they can be broken down into digested and used as nutrient stores of amino acids later. And so it can be used as anabolic means of making the structural components for muscles, i.e. proteins and muscles, or the amino acids can be converted here in that transamination to the ketone acids, and then essentially from there be converted into fatty acids or go through the rest of the sequence for energy, or they can be changed into structural components, protein in the liver as well, right? Now, if it goes through the keto acids goes and changes into fatty acids, basically those can be combined with glycerol to make triglycerides, then later can be stored as fat in adipose tissue. Glucose can also be converted into fatty acids and glycerols, thus triglycerides for fat stores. Or it can move through glycolysis and move into glyceraldehyde 3-phosphate into glycerol or glycogen stores so that we can store it as glycogen. And so these are all the major events and principal metabolic pathways of the absorbent state. Now, the absorbent state is basically modulated through hormonal controls. And the major controller or the absorbent state is controlled primarily by insulin. Insulin is secreted by beta cells of the pancreas. And it's stimulated by a couple things: elevated blood glucose levels and amino acid, or intestinal GIP, which is glucose-dependent insulinotropic peptides, in addition to parasympathetic stimulation, right? When insulin binds to membrane receptors, it facilitates diffusion of glucose into muscles and adipose cells. Now, there are a couple organs that can take up glucose without insulin, and those are the brain and the liver. Now, insulin is considered what's known as a hypoglycemic hormone. And if you've ever seen, it can kind of help you remember this, is if you've ever seen any kind of online weight loss, they always talk about the hypoglycemic index when you're talking about some of those pay weight loss, and they give you food and all of that. So that can kind of help you understand that. And so basically with this, it helps to enhance glucose oxidation. So how well glucose is broken down in glycolysis. The formation of triglycerides, gluconeogenesis, or glycogen, right? Active transport of amino acids into tissue cells itself, and protein synthesis. It also helps to inhibit glucose being released from liver cells and gluconeogenesis. So this is the process of, if you remember, taking other molecules and converting it into glucose. Up here, when we're talking about basically glycogen and triglyceride formation, this is the idea of making glucose to be, or other molecules like triglycerides, for later. Now, if we go and we don't have enough food later, you can take triglycerides and break them down into glyceraldehyde 3-phosphate, and then can be turned into glucose. And that's this process. But that only happens in kind of starvation, or when you're not in the absorbent state or the fed state. So this kind of gives you an idea. Insulin directs nearly all events of the absorbent state. So you have more blood glucose. This is going to stimulate the beta cells of the pancreatic islet cells to release insulin. So it's going to increase insulin, and then they're going to target cells. So it increases active transport amino acids into cells. So it can cause you to actually make proteins. And it's going to facilitate glucose to go into tissues. So here you're going to get cellular metabolism. And it can enhance basically fat stores and glucose stores, right? So that's what happens in the absorbent phase. Now, diabetes mellitus is if you have inadequate insulin production or abnormal insulin receptors. And so this can result in glucose not being able to get into most body cells. You'll end up noticing that you have excessively high blood glucose levels, right? And so all this excess glucose you have does get released into the urine. And some of the early indications of having this is that the urine would taste sweet. People would test that, imagine that job. Fats and proteins are used for energy instead, and so this can lead to metabolic acidosis. Remember, then you're having to break down proteins, and fats, creating ketone bodies, or protein wasting and weight loss. So the post-absorbent state is what's known also as the fasting state. So absorption is fed state, right? And this is when the GI tract is empty and energy sources are supplied by the breakdown of body's reserves. So you're seeing a catabolism of fat, glycogen, and proteins will exceed anabolism, right? So this is catabolism is higher than, right, anabolism, where in the fed state it's opposite. And so there are goals to maintain blood glucose between meals by basically making glucose available to the blood. And promote use of fat for energy. Now, there is this thing called glucose sparing, which I mentioned a moment ago. And this is basically the idea that we save glucose for the organs who need it most. So, which organ do you think would need it the most? Hopefully you said brain, because that would be right. So, let's talk about the different sources of blood glucose. So, you have glucogenolysis, which happens in the liver. This is the first reserve that's used. You have glucogenolysis in skeletal muscle. So before glucose from the liver is exhausted, we start getting breakdown here. Lipolysis in adipose tissue and liver. And so as we get this, we're producing basically glycerol and fatty acids. So here, this glycerol we produce is used for gluconeogenesis in the liver. And the last that we hit where we can get blood glucose from is catabolism of cellular protein. So this is a major source during prolonged fasting. There's only a limited amount that's available before there's damage to the body. And basically, a big thing, the amount of fat you have determines how long a person can survive without food. So, looking at here, the major events and principal metabolic pathways of the post-absorbent state, right? So when we're looking at this, gluconeogenesis in liver. So number one here, you have stored glycogen, right? And basically that's going to be broken down into glucose. And it can be released as blood glucose, and glucose sparing is making sure that that glucose gets to where it needs to go, i.e. things like the brain, right? Now, if you look at gluconeogenesis or glucogenolysis in skeletal muscle, which is 2, this is the idea of having glycogen in muscles. It gets broken down to pyruvic and lactic acid and moves here and can be converted into glucose again. Lipolysis in adipose tissue and liver starts in adipose tissue here, and you can see triglycerides can be broken down into glycerol or fatty acids. If it's fatty acids, it can be broken down to make ATP. An excess of ketones will build up, essentially an excess of acetyl-CoA will build up, right, and lead to ketone bodies. Now, acetyl-CoA, or these ketone bodies known as acetyl-CoA, can be used to make ATP in most tissues. Fatty acid and glycerol essentially can be broken down this way as well if you take them out and transport them to most cells. And catabolism of cellular protein, this is when the actual protein, not the glycogen stores in the muscles, are being broken down into amino acids. They can, through transamination, be changed into glucose, then essentially become blood glucose. So these are all the different ways of the 4 sources that I just talked about. Now, when I was talking about over here, glucose sparing, basically what happens is during prolonged periods of fasting, the body uses more non-carbohydrate sources to conserve glucose. More fat and proteins are converted to intermediates that can enter the citric acid cycle. But like I said, the brain does use a bulk of glucose, while other body cells can switch to fatty acids as fuel sources. The problem with this, it can lead to a bunch of ketone body production. Now, does this ever go into where ketones are being used by the brain? Yes. After about 4 to 5 days, ketone bodies will start being used in brain cells as fuel. So it's not optimal. They're going to try to use everything they possibly can before it has to go to that point. So, to continue with the hormonal and neural controls, but now let's look at it as a post-absorbic state. The sympathetic nervous system, those things that just automatically happen without us thinking, right, interact with several hormones to control events of the post-absorbent state. They're more complex than the absorbent state, right? And they utilize one hormone mostly, which is insulin. And so the post-absorbent state is triggered by a reduction in insulin. And this happens as blood glucose levels drop. Now, glucagon is another way to control. And this is known as a hyperglycemic hormone. It's stimulated by a decline in blood glucose levels, rising amino acid levels, and glucagon is going to promote a couple things. It's going to promote both glycogenolysis and gluconeogenesis in the liver, and lipolysis in adipose tissue that's going to cause fatty acids and glycerol to be released. Now, glucagon can also promote the modulation of insulin effects after a high protein low carb meal. And basically what can happen here is insulin responds to high amino acid blood levels. if so on here, right? To high amino acid levels, right? So if you consume a high protein meal, it's going to have really high levels of amino acid. And so basically what's going to happen is you're going to get a hypoglycemic condition. And that's not, you have a lot of proteins there, right? You have a lot of amino acids. But the problem is you don't have a lot of glucose there, and that's what your brain likes to eat off. So this is not good for the brain. And so at this point, it's going to help control this by basically glucagon is going to help modulate this effect. So it's going to ensure that you have the adequate amount of blood glucose. So let's look at this really quick and just look at how this post-absorbent state works. So here you can see the amount of plasma glucose is going to be reduced, but amino acid levels are going to start increasing. So basically, now the alpha cells of the pancreatic islet is going to release glucagon. So glucagon is going to stimulate in the liver glucogenolysis and gluconeogenesis. So taking glycogen breakdown, right, to make glucose, and then to make glucose from other stuff. So basically that's going to increase plasma glucose levels, inadvertently increase insulin levels. It can also go and stimulate lipolysis. And so you have lipids in adipose tissue. And so you're going to break those down. Remember, you can do it into glycerol and fatty acids. And basically that's going to cause fat to be used by other tissue cells, leaving glucose for your brain, or glucose sparing. And over time, this is going to help to increase plasma levels in the body. So this is a hypoglycemic hormone because it's going to increase the amount of glucose in the blood. If you think hypoglycemic index with insulin is going to decrease the amount of glucose that you see in the blood. Thus their naming. The sympathetic nervous system, besides hormones, can also help to regulate this. And so adipose tissue is innervated by sympathetic nervous system. So that can quickly supply glucose if blood levels are low. Basically, low plasma glucose, fight or flight response, or exercise can trigger fat mobilization and gluconeolysis, right? And that's important because you'll need more glucose in our body to allow for energy or ATP to be made to allow for activity to happen. And so that's activated or initiated by the sympathetic nervous system and ephedrine from the adrenal medulla. Other hormones, metabolism and nutrient flow are also influenced by hormones other than glucagon and insulin, right? Growth hormone, thyroxine, sex hormones, and corticosteroids can all have an effect on metabolism, but most are indirect effects. And so this kind of goes through and shows, and most of this we've talked about. So if you look at insulin and, if you look at insulin here and glucagon, this is a really nice table because basically it tells us everything we've already talked about. Insulin's going to help stimulate glucose uptake by the cell, stimulates amino acid uptake by the cell, It stimulates glucose catabolism for energy, stimulates glucogenesis, right? The glycogenesis that's going to help to basically make glycogen. Stimulates lipogenesis and fat storage. And it inhibits these guys because, sorry, I didn't read that. I was thinking something. It inhibits him because essentially you don't need to make glucose from other types of biomolecules because you have enough there already. And it's going to activate protein synthesis, right? None of these things happen here with glucagon. What it does is it helps to activate glycogenolysis, and this is the breakdown of glycogen. Stimulates the breakdown of lipids and to activate fat. And it says, hey, can we please here start making glucose from other stuff? If you can see, ephedrine activates those because it's it gets released from the adrenal medulla through the neuronal controls of the sympathetic nervous system. Growth hormone, well, we're getting bigger, so it's going to have to activate amino acid uptake, protein synthesis, and basically it's going to activate a few things to help get fats mobilizing for energy and to make glucose. Thyroxine, you can see, stimulates glucose uptake and catabolism or glycolysis, along with proteins synthesis and fat mobilization. Cortisol, the stress hormone, is basically stimulating the fat mobilization, gluconeogenesis, and the catabolism of proteins. And testosterone basically just has protein synthesis. And you can think a lot of times that people take or steroids injections to help with this. As you get older, you get less steroids, which is why you get reduced muscle formation. So this is just kind of some other hormones that are important. Now, this is basically the last small section of our body and how the role of liver is important in metabolism. So you have hepatocytes that carry out about 500 different metabolic functions here, right? It's crazy how much they're responsible for. They're important in process of early class of nutrients, or they process almost different class of nutrients. They play a major role in regulating the amount of cholesterol that's in the blood. They help to store minerals. And then in addition, they help to metabolize drugs, hormones, and bilirubin. And this just kind of gives you an overview on how the liver is important. In the body. And so basically, when we're talking about carbohydrate metabolism, and this is important in making sure we have the right level of glucose in our blood, that your liver basically is important because it can take other forms of sugar, like galactose and fructose, to make glucose. It's important because it's there to help store glucose as glycogen. And then later, it can help to release glucose to the blood when it breaks down that glycogen store. It's responsible for gluconeogenesis, which is converting things like amino acids and glycerol to actually glucose that can be then stored as glycogen and can be later released when we need it. And it can convert glucose to fat for storage. So the liver is pivotal, right, in carbohydrate metabolism. It's pivotal in fat because it's the prime site of beta oxidation, or the breakdown of fatty acids to acetyl-CoA. It converts acetyl-CoA to ketones. Helps to store fat. Helps to synthesize lipoproteins and cholesterol. Both of these we've already talked about. It's also important, this is kind of all over review at this point because I think we've talked about every single one of these. Without liver metabolism of proteins, you would have problems surviving. Many of the essential clotting proteins wouldn't be made. Ammonia would not be removed from your body. And so you could essentially get very, very sick. And so deamination occurs here. And without deamination, we couldn't essentially make ATP. We basically are able to synthesize urea to get rid of ammonia in your liver. It's important for synthesizing a lot of different plasma proteins, globulins, and some hormones. And think, when it doesn't work right, like in cirrhosis, it can cause things like edema. And transamination happens here. And so this is where we're converting some non-essential amino acids to be used as energy. In vitamins, it stores vitamin A. You can get 1 to 2 year supply here. It helps with vitamin D and B12 and stores iron. And you know iron is important for hemoglobin to transport oxygen around, right? And it's stored as ferritin because remember, having free iron going around your body is toxic. And biotransformation. This is what's important to make sure that our body isn't riddled by toxins. So it can metabolize alcohol, drugs, and other toxins by essentially making them inactive. And so they'll end up getting excreted by the kidney. It helps to process bilirubin, resulting basically, this is our red blood cell breakdown, excreting the bile pigments and bile. And it metabolizes the blood-borne hormones. Now, when we're talking about how metabolism works and what's important in your body to make sure that things are running properly, we have cholesterol there. Cholesterol is not used as an energy source. It's a structural basis of bile salts that we talked about, steroid hormones, and vitamin D. It's a major component of the plasma membrane, so it helps to keep the lipid bilayer fluid. Basically, about 15% of blood cholesterol is ingested, with the rest of it made in the body primarily by the liver, and we just talked about. And it's lost through the body whenever it's catabolized into bile salts, and that will be lost in the feces itself, right? So how do we transport cholesterol around? Because we're going to make it, then we need to get it into cells. And basically, it's transported using lipoproteins. And the lipoproteins are water-insoluble cholesterol and triglycerides that get attached onto these proteins to be able to move them around. So this is important because it helps to mediate or regulate lipids being able to get in and out of cells. All the lipoproteins are going to have things like triglycerides, phospholipids, cholesterol, and protein because those are a main part of the bilayer. And the higher the percentage of lipids, the lower the density is. So the high density lipoproteins essentially have the highest protein concentration. Whereas if we're talking about things like LDLs, now that you know that HDLs have the highest basically protein concentration, what do you think LDLs have? These are considered low density lipoproteins, and they have the highest cholesterol content. And we've already talked about very low density lipoproteins. And they are more than half triglycerides. With a low density of proteins. And what are chylomicrons? Basically, we get those transported from, right, the form that essentially comes from the lymphatic system on a way to move around fat, and it has the lowest density. And consists of entirely triglycerides. So now let's look at the combination, right? So chylomicrons come from the intestines, right? And here it's about 80 to 95% of triglycerides, a small amount of phospholipids, a small amount of cholesterol with minimal proteins, right? Very low density lipoproteins, as you can see, small amount of protein, small amount of cholesterol, a little bit more phospholipids, but mostly triglycerides. Very low density lipoproteins, you can see the triglycerides are tiny, right? More phospholipids, but they have an overabundance of cholesterol and having more protein than we have triglycerides. And the high density lipoproteins is a lot of protein, minimum amount of cholesterol, nice amount of phospholipids, and small amount of triglycerides. So let's look, now that we know how they're composed, let's talk a little bit about how they metabolize and regulate blood cholesterol levels and how they get stuff where they need to go. So basically on here, the VDLs are important because they transport basically triglycerides from the liver, right? You see the liver here, to peripheral tissue. Mostly things like adipose. The LDLs are important because they're going to transport cholesterol, this big guy, right, to peripheral tissues. And basically it's for things like membrane storage and hormone synthesis. This guy, the HDL, is going to basically transport excess cholesterol out. So it does it from the peripheral tissues to the liver. And then they're going to be basically broken down and secreted as bile. This guy will also provide cholesterol to steroid producing organs. To help make hormones, right? So, what's the recommended levels of cholesterol? About 200 milligrams per deciliter or less, right? Anything more than that can lead to atherosclerosis, which is a hardening, thickening of the arteries and blockage. The most important thing to measure is the form in which cholesterol is transported. HDLs are thought to be protected against heart disease because it's taking cholesterol out of the blood. So more than 60 is good, less than 40 means you're not having as much there to get rid of stuff. LDLs are considered not advantageous because they're depositing cholesterol in your vessels. So you want less than 100. Above 130 is not good. And hopefully it can give you an idea of how they're composed, why one is better than the other. Now, the factors that help regulate blood cholesterol levels basically is liver helps produce cholesterol as a basal level, regardless of dietary cholesterol intake. Just because you restrict cholesterol doesn't mean that you're going to reduce blood cholesterol levels. So basically, it's more important effect is relative amounts of saturated and unsaturated fatty acids. So saturated fatty acids stimulate the liver synthesis of cholesterol and inhibits cholesterol excretion from the body. Unsaturated is going to enhance cholesterol into bile. So unsaturated fatty acids are more advantageous to take or to eat. Trans fats can occur when healthy oils are chemically transformed into solids, things like margarine. They're going to have a worse effect on cholesterol levels than saturated fats. So this is going to increase the LDL, the ones that actually deposit cholesterol into the cells and arteries, and reduce what removes them, or HDLs. Unsaturated omega-3 fatty acids found in cold water fish have lowering proportions of saturated fats and cholesterols. This is going to make platelets less sticky and help prevent spontaneous clotting. It's also going to have antiarrhythmic effects on the heart and can lower blood pressure. Stress, cigarette smoking have been shown to level HDL, which are the ones that remove cholesterol, so you want to not smoke or try to modulate the amount of stress. Aerobic exercise and estrogen can increase HDL levels and decrease LDL levels. Body shape plays a role as well. So if you're an apple figure, which means you're rounded around the middle, fat carried on your upper body is correlated with high cholesterol and LDL levels. Or pear shape, if you carry most of your weight in the lower part of your hips and in your thighs, it correlates to lower cholesterol and LDL levels. And this can be such a problem because it can cause a risk factor for assessments of cardiovascular disease. Previously, high cholesterol and LDL-HDL ratios were used as predictors for potential diseases. It's not found to be as reliable. Now what they do is look at LDL levels and other risk factors to figure out your rate or your assessment or risk factor for cardiovascular disease, and they tend to be more accurate. Treatment with high LDL levels, like statins, which are cholesterol-lowering drugs, have helped, and it's estimated that greater than 10 million Americans take statin.